Photos of three different digital instruments on an automobile dashboard. Left, older odometer, middle, electronic odometer, right, holographic odometer. Figure 9. 1. Software engineering is used to develop solutions that are used in everyday life, such as controlling digital instruments on automobiles' dashboards to optimize the driving experience. Credit left. Modification of Flickr Nicholas T. Enduring by Nicholas A. Tonelli / Wikimedia Commons, CC by 20. Credit middle. Modification of Lexus LFA by Nan Pomero / Flickr, CC by 20. Credit right. Modification of M25 Orbital Approaching Bright Heads-Up Display by J. Galvin / Flickr, CC by 20. Chapter Outline 9.1 Software Engineering Fundamentals 9.2 Software Engineering Process 9.3 Special Topics. What is software engineering? Why is software engineering important? How is software engineering done? Well, software engineering impacts every industry and all aspects of life. One sector where software engineering has been revolutionary is the automobile industry. Software that has been written to automate the dashboard is being reinvented again and again to augment the driving experience with software solutions such as universal head-up displays for cars. These displays provide speed and navigation information at eye level and thus keep drivers from having to glance down at their dashboards while driving. Software is ubiquitous nowadays, and its presence is changing traditional industries. For example, software is more important than ever before in automobiles, and automobile manufacturers are responding by investing more and more on its development. The development of digital healthcare devices has similarly caused the healthcare industry to invest in software development. Even customer support operations are changing by utilizing generative AI, Gen AI software, such as ChatGPT to answer questions about diseases and how they spread. As spending on software development increases, traditional companies become technology companies in which software and its development play important and most often crucial roles. Advances in embedded systems, communication technologies, machine learning, and intelligent autonomous solutions, such as autonomous cars, large language models, e.g. ChatGPT, and insulin pumps and other wearable health technologies, will further boost this trend across most industries. Software engineering focuses on the design and development of software. As companies undergo digital transformations, software engineers must know and apply sound principles to the solutions they help create. They must collaborate with enterprise and solution architects and be familiar with software engineering lifecycle processes to address the needs of the companies they work for and to use approaches, techniques, and tools to design and develop meaningful software. As businesses evolve and technology changes, so do the expectations placed on a software engineer. For example, consider how an average automobile from 40 years ago had little to no software engineering in its operation. In today's automobile industry, software engineers are creating a variety of solutions that are incorporated throughout a vehicle. This ranges from the software running on interactive screens on dashboards that feature music systems and navigational aids to the software that allows for control of hands-free phone calling. As software engineering solutions in automobiles continue to evolve and be applied to all aspects of driving, they are paving the way towards self-driving, autonomous vehicles. Software engineers face many challenges because software engineering processes always need to be tailored to each project, and software engineers must be able to help understand, design, construct, and deploy software solutions that move that project forward. Thus, the process of developing software for an automobile that supports embedded features such as heads-up displays, lane departure systems, and even embedded solutions that alert the driver about mechanical issues such as low air pressure in tires would be quite different from that for a smartwatch that features applications that help users track their exercise and monitor their sleep patterns. While software engineers follow a process to derive the solutions they build, they must constantly adapt to handle issues and changes associated to the business environment they work within, as well as refine the technology and approaches they use. Software engineers also need to understand business requirements to ensure the software solutions they create are successful. This is made more difficult as requirements constantly change, or as people involved in a project have conflicting expectations. As anyone who has sent a text to a friend about dinner plans, only to discover that it has been changed to be a discussion of ducks and other ornithological matters, even a seemingly straightforward requirement like automatically correct misspelled words has multiple interpretations. Furthermore, assessing whether the misbehavior of solutions results from broken code or a misunderstanding of requirements often leads to confusion and disagreements between the software engineers and their customers. To minimize such issues, it is important for software engineers to understand their role and to familiarize themselves with software engineering processes, the types of solutions and technologies that are available, and their applicability to a given project at a given time. Consider a scenario in which a software engineer is working at a company called TechWorks. The engineering team they are part of is tasked with a project to add new software features to the dashboard of an upcoming electric automobile. Because the process of software engineering cannot, in general, be fully automated, software engineers face the challenge of having to determine the best software process, approaches, and tools to be used for the project. They must do so while collaborating with a number of people and facing changes in requirements, and they still have to deliver solutions on time and within budget. In the example of the automobile dashboard, the design and development of a new digital speedometer requires coordinated efforts from all the team members and their alignment with the same goals. Fortunately, as you will learn in this chapter, there are a variety of software frameworks and tools that the software engineering team can apply to a project to increase its chance of success. Learning objectives. By the end of this section, you will be able to describe the intent of software engineering and how it relates to computer science. Recognize various categories of software. Identify the skills that are required for a software engineer. This section introduces software engineering, along with the challenges associated with the creation and evolution of software. The various fundamental facets of software engineering are presented, including the skills required to properly engineer software and the role that a software engineer is expected to play within a software team. The intent of software engineering. The IEEE-1 defines software engineering as the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That is, the application of engineering to software. It is important to understand how software engineering fits into the larger context of computer science. It is also important to understand the role of a software engineer and how it fits within an organization. The reference to a systematic, disciplined, quantifiable approach does not mean a bureaucratic, document-laden approach. Software engineering relies on various methodologies, processes, methods, and tools that may be used to professionally develop and maintain quality software, while optimizing the use of resources such as time and cost. Selecting the right processes and methods for a project, and using tools to accelerate the ongoing development of a solution is challenging, especially when requirements are changing, and many software developers are working together to tackle a large project. Part of the issue is that software engineering as a process cannot, in general, be fully automated, and therefore it is difficult to keep all the activities aligned with the end goal of delivering a solution on time and within budget. Selecting and tailoring software engineering processes and methods, as well as using the right tools in the right fashion to meet this end goal, which in essence defines a majority of what a software engineer does, is covered in detail as part of this chapter. Concepts in practice. Software and our daily lives. Software is everywhere, and most of us interact with a software system on a daily basis. Yet the importance of software is expected to grow even greater in the coming decades. Although most software revenue comes from a generic software, software systems tailored to specific needs can be found everywhere, from our cars to our smartwatches. Thus, quite a few of us can expect that we will be involved as customers in some software engineering process during our professional lives. People who are familiar with concepts of software engineering can better oversee the projects they are working on by interacting with customers, so their needs are clearly specified, and by working with developers to smooth out the development process and ensure the final product meets customers' expectations. Software engineering teams. In most organizations, software is developed by a team of software engineers, as well as other people with different backgrounds and skills. To be effective, the project team must be organized in a way that maximizes the use of each person's skills and abilities and emphasizes the importance of teamwork to address all the aspects of the projects. This is especially true for complex projects. Effective project managers focus on problem solving and in product quality, and thus they may organize software teams in a variety of ways. The key factors considered when selecting a team organizational model are as follows: difficulty of the problem to be solved, degree to which the problem can be modularized, required quality, reliability, and other non-functional requirements of the system to be built. Delivery date, budget limitations, team lifetime i.e. overall period of time during which the team members will work together. During the creation of a software solution, software engineer team members may take on various roles, such as project manager, who is responsible for making sure that the project gets completed on time and on budget, enterprise or solution portfolio architect, who makes high-level design decisions on high-level modeling or solution, design building blocks and their interconnections to best address functional requirements, as well as non-functional ones, such as performance and usability. User experience (UX) designer, who plans how users will interact with the software system. This involves tasks like designing the user interface (UI), making wireframes and prototypes, and conducting user testing to ensure the software is user-friendly and meets user needs. Software developer, who analyzes requirements, refines the design, writes and tests code, and collaborates with the operations team to deploy the software into testing and production environments. Quality assurance tester, who checks for bugs and validates that the system meets the requirements. It is common for one team member to act in several roles. For example, a solution architect might also be a software developer. And some roles may be filled by multiple team members. For example, there are typically multiple software developers on a project. Additionally, a software engineer may work directly with other people, including product owners, who are generally project sponsors and provide the requirements and overall guidance on what is expected from the solution. Subject matter experts, SMEs, who are specialists in areas such as business, technology, products, or other topics as needed. Database administrators, who focus on areas such as data storage, organization, and access associated with a software solution. Operations specialists, who are IT and/or DevOps professionals with a focus on computer hardware and software operations. Because projects can involve a large number of people working in many different roles, communication and interaction among team members is critical for a project to succeed. To keep the team running smoothly, projects are ideally structured so they include the following: deadlines that provide sufficient time for team members to fully complete their tasks and ensure results that match the requirements. Standards for how business and technology decisions are made to avoid business or technology-related disagreements. Processes and procedures that make it easy for team members to coordinate their activities. Clear definitions of each team member's role and authority so that everyone knows who is accountable for each task and where questions should be directed. Cost management. An important part of the role of a software engineer is to handle the project management triangle of timeliness, quality, and cost. The goal is to deliver projects as quickly as possible with the highest quality and the lowest cost. Doing this requires good communication, planning, and focus, as well as the setting of realistic expectations. Furthermore, because the cost of maintaining a software solution over time can be significant, various cost management strategies must be used to manage costs effectively. These strategies include the use of estimation techniques, resource allocation, and cost tracking tools. Estimation techniques help create accurate estimates of project scope and effort and cost, which helps with budgeting and resource allocation. Resource allocation involves assigning the right people, i.e., those with the necessary skills, to complete each task, and this helps optimize efficiency and cost. Cost tracking tools help track project costs and identify areas for potential savings. The ongoing evolution of computing technology, such as web, mobile, and cloud computing, has had a significant impact on the way modern software engineering is done. Nevertheless, it is still common to get into trouble when designing and developing high-quality software on time and within budget. The major reasons for that are as follows. Software systems are the most complex types of systems humans create. The pace of change in computer and software technology is high. The programming techniques and related processes that work well when used individually or in a small team fail when applied in a large team developing a large complex system. There are not enough qualified software engineers, and thus software systems are designed and developed by people who have insufficient backgrounds or experience. Software engineering and computer science. Where does software engineering fit within computer science? Both software engineering and computer science deal with the creation of software, And while there appears to be an overlap between these two disciplines, software engineering tends to focus on software applications, more specifically, on the design and development of software solutions. This makes software engineering a branch or subarea of computer science. Computer science focuses on the study of algorithms and their realization in terms of computers, computer systems, and related computational processes. It focuses heavily on the theoretical and mathematical principles involved with the creation of algorithms and data structures. While computer science includes software engineering, it also covers a variety of other disciplines. In comparison, software engineering focuses specifically on the application of engineering principles to understand, design, construct, and deploy production software. It starts with eliciting and analyzing requirements and results in providing a practical software solution that meets those requirements. Computer science goes beyond just creating software solutions and includes software design and development. While software engineers need to have a solid knowledge of fundamental computer science, e.g., the basics of algorithms and data structures, they are not expected to exhibit the same level of theoretical knowledge as that of a computer scientist. For example, while a computer scientist would need to be able to establish the asymptotic time complexity of the algorithms they pick, a software engineer would not. Software engineering departs from the general focus of computer science and is complementary in the following ways. Software engineering tends to focus on applying technology to create solutions, whereas computer science tends to focus much more on understanding the technology itself. Software engineering tends to focus on software. Computer science can focus on software, hardware, and the interaction between the two. A software engineer tends to focus on developing solutions that meet the requirements of an organization or project. A computer scientist tends to focus on the underlying computational processes required to create solutions in the optimal or most efficient ways. The essence of the software engineering practice is based on the work of numerous researchers, such as the mathematician George Polya. Polya's heuristic for generalized problem-solving includes the following steps: understand the problem, devise a plan, carry out the plan, look back and examine the solution. The nature and impact of software. Software has become an essential part of our lives. It has revolutionized how we communicate, work, learn, and entertain ourselves. From the smartphones in our pockets to the complex systems that power hospitals and transportation networks, software is everywhere. Because the focus of software engineering is to build software, it is important to understand what software is. A piece of software is made up of instructions that can be executed and generally includes documentation that describes the software operation and use. These instructions tell computers what to do. They function like a recipe that tells a chef how to cook a meal. Software is designed to accomplish a specific objective or purpose. Word processing software has the objective or purpose to help people create documents. A game has the objective or purpose of providing entertainment. The software built into an automobile has many purposes, including helping a driver drive the car, helping the owner maintain the car, and helping a driver and/or passengers avoid getting lost. Software is generally created based on a set of requirements, and although software does not wear out, these requirements often change over time. Software must, therefore, be updated often to respond to these changes. In addition, software can contain defects, i.e., bugs, which are expected to be fixed in a reasonable time after they are reported. Over the years, software engineering researchers and practitioners have converged on defining a generic software engineering process model, or process framework, that can be used as a template to characterize the generic activities performed by all the software engineering process models that are used to support the software development lifecycle, SDLC. The SDLC is a structured set of the framework activities required to develop a software solution based on a set of requirements. A process framework generally encompasses 4 framework or generic activities: inception, elaboration, construction, and deployment. These activities are also known as phases. You'll learn more about each of these phases later in the chapter. In the meantime, it should be noted that the deployment phase covers integration and user acceptance testing, installation, and maintenance support activities. This means that maintenance is an integral part of the software engineering process. In fact, the cost of software maintenance continuous deployment today often exceeds the cost of software construction, especially if software remains in use for a long time. Categories of software. There are 3 main categories of software. Software that enables you to control hardware and provides an environment in which other software can run is called system software. An example of this is an operating system, such as Microsoft Windows, Android, and macOS, which runs on a laptop or a mobile phone and typically controls and provides access to the computer's basic functionality. This system software also includes driver software, which is the code used by hardware devices to interact with the operating system. Software that enables you to fulfill common tasks, such as creating a text document, drawing a picture, or playing music, is called application software. Examples include Microsoft Word and Paint, macOS Pages, and iOS files. Application software may include specialized categories of software such as scientific or engineering software, which is software that aids you in solving mathematical, scientific, and engineering problems, such as finding the roots of an equation. It can also include software services, which are software programs that provide specific responses or actions based on a request, such as returning stock quotes, obtaining weather conditions, or finding what current jobs are available. Software that is integrated with hardware and can include both application and system software features is called embedded software. Examples include software in a smartwatch, an automobile control system, or microwave. Interaction with embedded software is usually limited, and users are often unaware that they are interacting with software. With the increased popularity of the Internet of Things, IoT, embedded software development is increasing. Software engineers must often deal with legacy software that has been written in the past, relies on obsolete technology, and is still in use today. This software presents special challenges to those who maintain it, especially when they need to adapt it to a new computing environment or technology, and when they are to extend its functionality so that it is interoperable with new software systems. The need for software maintenance of legacy software stems from the rapid changes that have taken place in hardware. For example, a common smartphone contains a more powerful processor and more memory than computers that were used just 20 years ago. Changes in hardware are accompanied by changes in software technologies, and these are quickly adopted by users who are then reluctant to use legacy software in its original shape. For example, the graphical user interface of a software system that was developed 20 years ago now looks outdated and leads to an unpleasant user experience. There have also been dramatic changes in processor technology. 20 years ago, most processors consisted of a single core, while now it is common for a processor to have multiple cores and coprocessors. This requires changes in how software is programmed because software that can utilize multiple processor cores has a competitive advantage compared with software that uses only a single core. To support these new capabilities, major programming languages have evolved towards supporting multithreading, which makes maintenance of a legacy code base even more challenging. Concepts in practice. The ever-changing world of software platforms. Imagine the life of a software engineer developing programs in the 1980s, which required typing programs on a terminal and printing punch cards that were fed into a mainframe computer. The world of software development is constantly evolving, and the platforms where software runs change rapidly, too. Software engineers need to stay up to date on current platforms and also become aware of what is coming next. A trip through time. Can you imagine using a computer without a mouse or a graphical interface? Let us take a look at the way software platforms have evolved over time. Early days, 1980s. Mainframes and mini-computers were giant, even room-sized, and software was often run from the command line. The rise of the desktop, 1990s. Welcome to the age of Windows and Mac. Graphical interfaces made computers more user-friendly, and client-server systems allowed applications to run across multiple machines. The web takes over 2000s. The internet exploded, and Java and C# became popular languages for building web applications. Mobile mania, 2010s. Smartphones like the iPhone changed the game. Software development focused on mobile apps that took advantage of constant connectivity. The future is unknown but exciting. Augmented and virtual reality, AR/VR, machine learning, ML, artificial intelligence, AI, the Internet of Things, IoT, and blockchain are some emerging technologies that are shaping up the future of metaverse software platforms. Who knows what exciting new platforms await? Curious and adaptable software engineers will be best positioned to thrive in this ever-changing landscape. Software requirements. Software is developed based on requirements, which are categorized as functional and non-functional, as shown in Figure 9.2. Functional requirements state what the software needs to do in terms of tangible functionality, such as the login or registration functionality that allows users to access a given piece of software, such as their Facebook account. Non-functional requirements are measurable qualities of a piece of software, such as usability, performance, and other quality aspects. Hierarchy chart of software functional and non-functional requirements. Figure 9. 2. The various types of software requirements can be organized in hierarchies as functional and non-functional requirements based on aspects that relate to what the software does along with the qualities of the software. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. As noted earlier, a functional requirement relates to the services the system provides to the users. It reflects the user's expectation about the inherent characteristics of the software, i.e., the functions it must perform. Functional requirements can include those phenomena that are generally seen or done when using a software solution, such as the information that is entered or that is generated by the software, the authenticating rules for using the software, or whether there should be an audible alert, such as a beep when an action is selected. A non-functional requirement describes a desired quality or feature, i.e., constraint, and covers aspects of the software such as flexibility, maintainability, performance, portability, reliability, scalability, security, and more. For example, a non-functional requirement could specify that responses from the software must occur within a specific time frame, or that a software system must be able to handle a certain number of transactions at any given time. Another example of a constraint that a non-functional requirement may express is the need to use a specific programming language or follow a particular standard. Non-functional features are sometimes categorized in terms of static or dynamic qualities. A static quality is a non-functional feature that is unchangeable and thus might be associated, for example, with the source code and related documentation, or with legal or project environment-specific requirements. A dynamic quality is a non-functional feature that relates to the qualitative behavior of software while it is in use, which means that it also depends on the hardware that the system runs on. Both quality types are measurable features rather than functions that are present or absent. Examples of static qualities include maintainability, which is a measure of the amount of work required to fix bugs, improve performance, and keep the system running. Extensibility, which is a measure of the amount of work and cost of adding new features to software. Flexibility, which is a measure of the difficulty of updating the system to meet changing requirements. Portability, which is a measure of the amount of work and cost of migrating software solutions. Usability, which is a measure of how intuitive the user interface is. Examples of dynamic qualities are performance, which is a measurement of how quickly the system responds to requests it receives. Throughput, which is a measure of how much input the system can process within a given time frame. Availability, which is a measure of how often the system will be ready and active for users. Scalability, which is the measurement of the work and cost to increase a system's throughput. Security, which is a measure of confidence that data is protected from unauthorized disclosure and that systems are protected from unauthorized access. The relative importance of the preceding characteristics depends on the solution requirements and the environment in which they are to be used. For example, in an internet banking application, availability and usability are typically key features advertised to customers. Security would also be important, as the software solution would need to comply with regulatory requirements. In a brokerage system, performance would be an important requirement because the software system will need to display prices and process users' orders in real time. Think it through. Professional responsibility in software engineering. Given the professional responsibility of software engineers working on various projects across the world, what is right or wrong, in your opinion, about the following matters in a software engineering context? Developing systems for the military, e.g., creating an autonomous military drone, adding a backdoor to an existing system, e.g., providing authorities with a way to unlock a locked mobile phone, or modeling patient medication needs, e.g., prescribing pain medication for each hospital patient based on historical data. In each of these cases, the development of the system could provide real benefits. For example, an autonomous drone allows the military to act without putting its soldiers' lives at risk, and a backdoor ensures law enforcement officials can get access to information they may need to solve a crime. But there are also drawbacks to each of these systems. The backdoor risks everyone's privacy because anyone could use it to access private data on a phone, and relying on past medication data risks institutionalizing existing biases about who needs more or less pain medication. It is important for software engineers to consider all of the impacts that a system will have and determine whether these impacts are acceptable or not. Software engineer skills. As mentioned earlier, a software engineer is involved in the creation of software. Software engineers work with others and are a part of a team. They must be able to understand and act on a vast array of requirements. To accomplish what is required, a successful software engineer must have strong analytical and problem-solving skills, must communicate well with their peers, must be a team player, must take responsibility for their commitments, must exhibit attention to detail, and must be pragmatic when adapting software engineering practices based on circumstances. In addition, software engineers must be flexible when it comes to adopting new technologies. Therefore, in terms of technical skills, software engineers must have a solid foundation in the following areas: problem-solving and algorithms. Software engineers are like detectives who solve puzzles. They use algorithms, which are step-by-step instructions, to efficiently solve problems. Understanding different algorithms allows them to choose the best approach for a specific task. There are many algorithms that can be considered essential, and it can be hard to learn all of them. Understanding the importance of algorithms and being willing to learn new things is a required skill for software engineers. Data structures. Imagine a well-organized toolbox where each tool has its designated spot. Data structures are like these toolboxes, but for data. Knowing different data structures, such as arrays, lists, trees, stacks, and queues, and being able to assess their benefits and drawbacks helps software engineers organize information efficiently for their programs. The knowledge of fundamental data structures is essential because without efficient data structures, you cannot write efficient code. Programming languages. There are many programming languages, and each one of them has strengths and weaknesses. Software engineers should be familiar with at least a few core languages, such as Java, Python, or C++. Most important, they should be adaptable and willing to learn new languages as needed. Software engineering process. Software is usually developed in a team and follows a process. This process describes how to organize a team of developers effectively, as well as how to approach the creation of the software. There are many approaches to team-driven software development, and software engineering processes can be either continuous or discrete. Discrete processes, such as those advocated by Agile Development 2, encourage flexibility as to what activities are required and to what degree within a given project. Usually, all activities will be conducted when using continuous processes. A software engineer should be familiar with the pros and cons of various software engineering processes to be able to apply the best one to their own software development projects. Later in this chapter, both traditional and agile software development lifecycle (SDLC) processes and various related models and frameworks are covered in more detail. Testing. The purpose of testing is to ensure that a software system is free of defects and meets the functional and non-functional requirements. It is important to realize that testing is an ongoing activity that occurs throughout the software engineering process. For example, software engineers may conduct unit testing of a website's checkout functionality as part of their software construction activities to make sure that the software calculates the total of a customer's order correctly. They may also be involved in integration testing as components developed by other team members are being integrated. Tools. There are many tools that can be used in software development, and these tools go beyond just being used to create software code. They can, for example, facilitate communication within the team, help support engineering tasks, and maintain a historical record of source code versions. Each software engineer should be familiar with major tools and their underlying principles so that they can use them effectively. Computer technology. Software engineers need at least a high-level understanding of the computer technology that might be applicable to the software solutions they may be required to create or work with. This includes areas such as operating systems, cloud services, security, networking, communications, database technology, and UI/UX. Software engineers might also be called upon to work with computer technologies such as machine learning, ML, and its applications to artificial intelligence, AI, business intelligence, BI, and the multitude of ever-evolving applications of computer technologies that are available today. A successful software engineer is aware of current computer technology and understands how to leverage it. Soft skills. A software engineer should have the soft skills required to assume their role, such as problem solving, communication, and time management, as shown in Figure 9. 3 soft skills tend to be more innate, but are often just as critical as the previously listed skills. For example, a software engineer could be tasked with developing a software solution within 12 months that tracks and displays relevant driving information onto a heads-up display presented on the windshield of a new model of an automobile. To deliver this solution on time, the software engineer would need to manage a schedule. As part of a team project, they would also need to understand how to effectively communicate and interact with other project team members. Additionally, they would need to solve the requirements to derive a solution using appropriate algorithms and patterns. Problem solving includes understanding how and when to bring subject matter experts or non-software engineer resources onto a project. Being able to apply these softer skills can be just as critical to a software engineer's success as applying the right processes, methods, tools, and data structures algorithms. Chart of soft skills required by software engineering: problem-solving skills, time management, ability to multitask, ability to work in a team, communication skills, aptitude. Figure 9. 3. These are some of the soft skills required by software engineers. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Technology in everyday life. Programming languages. A software engineer's toolkit. Imagine a toolbox with specialized tools, a hammer for carpentry, or a paintbrush for art. Software engineers also use various tools, and some of their tools are programming languages. Just as the right tool makes a job more accessible, the correct programming language helps engineers build different software applications. Can you guess the language? Identify the programming languages commonly used to build the following types of applications: mobile app, like Instagram; website, like Wikipedia; video game. Possible answers include JavaScript, Python, C++, Java. Why so many languages? Each programming language has its strengths. Some languages are great for building an application's core functionality, like C++ or Java, while others are better suited for adding interactivity, like JavaScript. Understanding different languages allows software engineers to choose the right tool for the job. How many languages should a software engineer know? There is no right or wrong answer to this question. It is possible, though not common, to be employed as a software engineer knowing only a single programming language. Typically, however, successful software engineers understand the different categories of programming languages and the common structure and design features of each. It is often recommended that a software engineer learn a primary programming language that can be used for system-level programming such as C, C#, or C++. Additionally, in today's world, a software engineer should understand object-oriented programming, which is done in languages like Python, C++, and Java. Because web development often is a part of solutions, knowing a scripting language, such as JavaScript, Python, PHP, Perl, or Ruby, is also beneficial. Finally, understanding markup languages such as HTML and XML is also important. Of course, the best languages to know are dependent on the projects that are worked on. If a software engineer is creating embedded solutions, then the programming language is likely going to be much different than if they are doing high-end gaming solutions or web-based solutions. Chapter 7, High-Level Programming Languages, delves deeper into programming languages. Learning objectives. By the end of this section, you will be able to describe the phases of a software development process and their purposes. Study the popular traditional prescriptive and agile software process models. Suggest an effective software process. Imagine a recipe for building software. There are different ways to cook the same dish, but most recipes follow a basic structure with steps like gathering ingredients, preparing them, cooking, and serving. Software engineering processes are similar. They provide a structured approach to creating software applications. Various software engineering process models are typically used to support the software development lifecycle, SDLC. After years of research and refinements, software engineering researchers and practitioners have converged on defining a generic software engineering process model, or process framework, that can be used as a template. That process framework includes a set of process elements, e.g., framework activities, software engineering actions, task sets, work products, quality assurance, and change control mechanisms that may differ for each process model and for each project. Traditional process models. One common category of process models is known as the traditional process model. This process framework, as you learned earlier in the chapter, encompasses 4 framework, i.e., generic activities that are also known as phases, Inception, elaboration, construction, and deployment. Inception covers planning activities where you define the project goals and identify the overall scope. Elaboration involves analyzing requirements and designing a detailed architecture model for the software. Construction is where the coding happens. The software is built based on the design created earlier. Deployment is the activity that focuses on releasing the software in a usable form and making it accessible to end users. These generic framework activities or phases are applicable regardless of the specific software engineering process model chosen for a project and may be elaborated differently depending on the organization and the problem area and project being developed. There are also umbrella activities that are important but tangential to framework activities. Returning to the recipe analogy, if generic framework activities represent cooking, then you can think of these activities as the things you would do alongside your cooking, like making sure you have the right pots and pans or keeping your kitchen clean. As you'll learn later in the chapter in software development, such activities are known as umbrella activities, and they include training and communication, e.g., work product preparation and production, risk management and planning, e.g., software project tracking and control, configuration management, quality management, e.g., technical reviews, estimations, metrics measurements, testing, architecture management, e.g., reusability management, security management. Various software engineering actions are typically performed as part of the generic framework and umbrella activities. For example, the inception phase may call for requirements engineering actions, such as requirements definition and requirements management. The elaboration phase may involve high-level and detailed design actions. Each type of software engineering action corresponds to a process that may be represented as a workflow or a task set, and each task results in work products that are subject to specific quality assurance and change control mechanisms. Basically, a task set or workflow encompasses all the tasks that are required to accomplish a specific software engineering action within a framework activity. Task sets vary depending on the characteristics of a project, and activities within a given process model usually overlap instead of being performed independently. Software process models that adhere to the generic framework mentioned precedingly are sometimes referred to as SDLC methodologies. In general, software engineering process models are structured in this fashion to facilitate efficient development of quality software, reduce risk of failure, increase predictability, and capture best practices in software development. The software framework provides a template that allows software engineers to tailor their process model based on the specific project on which they are working. The generic framework activities mentioned precedingly are applicable to all projects and all application domains, and they are a template for every process model. Actual process models' action methods may, however, use various approaches. Furthermore, software engineering tools may be used to semi-automate the various methods that perform activities. The activities involved in developing software might vary depending on the organization and the type of software being developed. There is no single right way to create a software solution, but experience typically tells us what works well and what works poorly in a given context. Therefore, process frameworks are elaborated differently depending on the 4Ps, problem, project, people, and product, they tackle. In the past, this led to the use of various traditional prescriptive process models, such as the waterfall, prototyping, spiral, and rational unified processes. A prescriptive process model advocates an orderly approach to software engineering that involves following a prescribed set of activities in a continuous manner. These traditional process models provide a structured approach to software development and may help with the following objectives. Improve efficiency. By following a clear plan, teams can work more efficiently and avoid rework. Reduce risk. Identifying and addressing potential issues early on can help to prevent project failures. Increase predictability. A structured process can help to estimate timelines and costs more accurately. Capture best practices. Traditional models often incorporate tried-and-true methods for software development. These days, however, traditional prescriptive process models are perceived by some as old school, i.e., ponderous, bureaucratic document-producing machines. Note that prescriptive simply means that the process model identifies a set of process elements, e.g., framework activities, software engineering actions, tasks, work products, quality assurance, and change control mechanisms for each project. Traditional models are generally criticized for being too rigid and inflexible. They may not be suitable for all projects, especially those with rapidly changing requirements. In general, the various process models may have features in common with each other, and there may be some overlap among the activities conducted within each given process. In the next section, we'll explore an alternative approach called Agile Software Development, Agile Process Models. The Agile Manifesto sets forth the Agile philosophy and emphasizes the fact that software engineering processes should not be constrained to be continuous. It advocates that it is fine to skip and accelerate framework activities to deliver a project solution faster, and therefore, it is fine for the software process to be viewed as a discrete set of meaningful activities to reduce the cost of change. In this context, agility refers to the ability to create and respond to change in order to profit in a turbulent business environment. Proponents of agile process models question whether prescriptive process models that strive for a structured and ordered approach to software engineering are appropriate for a world that thrives on change. In general, agile processes have very short product cycles and constantly solicit customer feedback to focus development on customers' current needs. Agile software processes promise strong productivity improvements, increased software quality, higher customer satisfaction, and reduced developer turnover. Agile development techniques empower teams to overcome time-to-market pressures and volatile requirements. However, replacing traditional process models with something less structured may make it difficult to achieve coordination and coherence in software work. In general, the mere existence of a software process, whether it be strongly prescriptive or agile, is no guarantee that software will be delivered on time or meet the customer's needs, or that it will exhibit long-term quality characteristics. Everyone wants a process that can respond to change. The only debates are over how to design one and which level of discipline should be incorporated into such process models. Agility requires that customers and developers act as collaborators within development teams. The goal should be to build software products that can be quickly adapted to meet the requirements of a rapidly changing marketplace. This is typically achieved via incremental development of operational prototypes that are improved over time. As a result, agile software engineering is a way of working, and it leverages iterative development, incremental delivery, and ongoing reassessment of products. It is based on a clear idea of the product's concept and its market. It also focuses on high-value features first and on producing tangible working results after each iteration. Agility principles are summarized as follows: ensure customer satisfaction by delivering software to customers as quickly as possible. Accept the fact that requirements may change and work accordingly. Deliver software incrementally to stakeholders as often as possible, e.g., every week rather than every month as it is in the case of traditional process models, and use their feedback to improve subsequent increments. Minimize the creation documentation to what is absolutely necessary and relevant. Build an agile team that includes motivated participants and facilitate frequent meetings among team members to improve communication and information sharing. Create team processes that encourage technical excellence, good design, and simplicity while avoiding unnecessary work. Focus on the primary goal of delivering software that meets customer needs. Ensure that teamwork is not overwhelming so that team members can be effective over a long period of time. Consider the fact that agile teams need to become self-organizing in order to meet the primary goal of developing solutions that are well-designed and implemented to meet customers' needs. Instill a team culture that requires all team members to work together with one focus in mind, which is ensuring customer satisfaction. The agile philosophy is seductive, but it must be tempered by the demands of real systems in the real world. In general, agile process models are not suitable for large, high-risk, or mission-critical projects. There is a spectrum of agility that one should consider that addresses these demands as illustrated in Figure 9.4. Graphic of spectrum of agility ranging from fixed process, less collaboration, rigid delivery through waterfall, hybrid agile and agile teams, to flexible process, more collaboration, incremental delivery. Figure 9. The spectrum of agility depicts traditional prescriptive process models such as waterfall on one end and agile processes on the other. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. When an agile software development ecosystem, ASDE, which encompasses the whole category of agile SDLC frameworks and methods, is compared with traditional, prescriptive, SDLC methodologies, the ASDE emphasizes the difficulty of predicting future needs. Thus, agile approaches avoid creating long-term plans and fixed processes, so developers can instead collaborate with customers and adjust to their current needs. Many of the ideas related to the Agile approach are worth considering regardless of the process model a team adopts. Agile processes manage unpredictable changes that take place during software development projects. The focus of Agile processes is on the delivery of software increments in relatively short time frames and using feedback on those increments to drive development. There are trade-offs when selecting an Agile software development ecosystem, ASDE. While ASDEs correctly identify the product as the most important outcome of a project, it can be difficult to scale up rapid product cycles to develop enterprise-wide software applications. In general, trade-offs are important for making things work. In particular, the potential problems caused by dysfunctional teams can be significant. The impact of human aspects of process model adaptation should be considered, and all the human factors and group dynamics of Agile teams, including collaboration and self-organizing teams, are important improvements to traditional approaches and are used repeatedly when Agile development is performed. In conclusion, a software process, regardless of its process centricity, simply must adhere to a set of software process model criteria that are essential to ensure successful engineering of software solutions. To that extent, it is necessary to assess processes and their related activities using actual numeric measures or by applying metrics as part of analytics methods used to monitor the performance of software process models. Software process framework activities. A good portion of a software engineer's role is spent within the various framework activities of an SDLC. As such, it is critical for a software engineer to understand the key elements of each of the various framework activities that are used to create software solutions. As you may recall, these framework activities or phases were introduced earlier as inception, elaboration, construction, and deployment. These activities provide a structured approach to creating software solutions. By understanding these framework activities and the tasks involved in each phase, you will be well equipped to contribute effectively to the software engineering process. Inception framework activity. A core precondition to the creation of a solution is to know what must be developed. It is easy to say you want to add automation features to an automobile, but what does that really mean? What are the specific expectations, and how do they relate to the solution that needs to be created? In order to create a solution, you have to understand what the solution is expected to do. The inception phase of a project focuses on the gathering and refinement, i.e., definition as well as the management of functional and non-functional requirements, which is also known as requirements engineering. In essence, the inception phase covers the planning activity that lays a project foundation. Here you will define the project goals, identify the overall scope of the software, what features it will have, and conduct feasibility studies to assess if the project is realistic and achievable. As an example, imagine you are building a recipe app. In this phase, you would decide what features the app should have, like searching for recipes or creating grocery lists, and estimate the time and resources needed to develop it. Defining requirements must involve stakeholders because they know what the software system should do better than others. Requirements definition involves obtaining the requirements from stakeholders and analyzing decomposing strategic requirements until you can identify tactical actionable requirements. These will form a foundation for the creation of the analysis model. This definition process is done with either a use case, which describes how the software system is expected to be employed by users to accomplish a goal or requirement, or as a user story, which is a generic explanation aimed at the user to tell them how a software feature works. Requirements management relates to handling changes in requirements and identifying the effect of such changes on the existing set of engineered requirements. Although the software engineering actions and task sets that relate to the drawing forth of requirements may appear straightforward at first sight, it is in fact one of the trickiest parts of the SDLC. This is due to a gap that always exists between the way stakeholders and business analysts understand the requirements as compared to the way they are perceived by software engineers. This is especially true when you develop a software solution for a particular expert group that use their own terminology. Often those who perform a process take some of the actions they do for granted. The inception phase results in a specification of the system to be developed. This specification is generally incomplete and/or anomalous and is typically refined as part of subsequent process phases or iterations of such. As a result, there is a blurred distinction between requirement specification, design, and construction. The actual software engineering actions and task sets that are used as part of the inception phase involve gaining an understanding of the solution context and collaboratively gathering, decomposing, and tracking requirements to help elaborate a preliminary analysis model. Once the preliminary analysis model is created, requirements can then be negotiated and validated with the stakeholders via an in-person joint application design (JAD) session, an approach that involves assembling stakeholders and developers, or through the use of collaborative requirements modeling tools that enable scenario-based modeling. After this, detailed requirements modeling takes place. Agile requirements definition attempts to accelerate the gathering and analysis decomposition of requirements. The guidelines it uses to speed this process include: use simple models such as fast sketches and user stories to allow all stakeholders to participate. Adopt user, client, or expert group terminology and avoid technical jargon whenever possible. Get the big picture of the project done before getting bogged down in details. Refine requirements throughout the project and allow additions and revisions to occur at any time. Implement the most important user stories first and only once its requirements are fully specified. Make the current set of requirements available to all stakeholders so everyone can participate in selecting the features to add during the next development cycle. Various tools may be leveraged to support the software engineering actions and task sets that pertain to the inception phase, e.g., RecView 3, requirements modeling. The software engineering action that is part of the inception phase and focuses on the analysis decomposition of software requirements is called requirements modeling. The goal of this action is to answer the question, what will the system do? The focus is purely conceptual, and implementation details are not considered. The main purpose of this analysis is to understand the requirements at a level that makes it possible to design and implement a software system that meets the customer's needs. As part of requirements modeling, as in business use case modeling, you typically create a domain model that captures the major concepts of the problem domain and associations between them. For example, in the domain of driving assists for an automotive solution, there could be conceptual analysis classes such as adaptive cruise control, car, blind spot detection, and blinker, and class attributes assigned to classes as follows. Adaptive cruise control has attribute state on-off and desired speed, the requested speed. Car has attribute speed, the current speed. Blind spot detection has attribute state on-off. Blinker has attribute state on-off. Figure 9.5 illustrates a class diagram of a partial domain model. This diagram is specified using Unified Modeling Language, UML. UML is often used for modeling in projects, as its visual representations provide clear, compact means of communicating among the developers. In UML class diagrams such as this, the numbers at associations are multiplicities, and the arrows specify the direction in which you are expected to read the association. For example, blind spot detection monitors car. Illustration of a class diagram of a partial domain model using Unified Modeling Language for adaptive cruise control. Figure 9.5 A UML class diagram, in this case of a partial domain model, is used as a communication tool among developers. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Associations are links that deserve to be stored in the system. For example, an association between adaptive cruise control and car is required because when adaptive cruise control is active, conceptual class adaptive cruise control needs access to the car. The numbers at associations are multiplicities, and they say that there is exactly one car associated with each adaptive cruise control, and that there is exactly one adaptive cruise control associated with each car. Associations can have names, which facilitate reading and understanding the analysis model. The UML notation may be applied to provide different perspectives as follows. Conceptual perspective. The diagrams describe real-world concepts or things. Specification, software perspective. The diagrams describe software components. Implementation, software perspective. The diagrams describe software components in a particular technology, such as Java or .NET. We typically use all perspectives throughout the software development lifecycle. Conceptual perspective to capture requirements, specification perspective to describe the design, and implementation perspective to clarify implementation details. When doing requirements analysis, you can create specific outputs work products, also referred to as artifacts, such as use cases, scenarios, and the domain model. Use cases can be captured in plain text or via a UML use case diagram. A use case diagram consists of an actor, which represents users of the system, and the use cases that this user is expected to use. In Figure 9.6, the actor is a driver who might be seeking to turn on cruise control. Each use case is then described in detail using one or more scenarios. A scenario is a specific instance of operational flow within a use case that is focused on understanding a specific action. Scenarios are written either in a plain text or as a sequence of steps that describe a specific scenario instance within a use case. I.e., main scenario describing the most productive set of steps versus alternative scenarios that capture unexpected behavior. Illustration of a driver and 3 use cases. Start adaptive cruise control, modify adaptive cruise control, and stop adaptive cruise control. Figure 9.6 in this UML use case diagram illustrating an actor called driver. The 3 use cases might be further grouped together and categorized as car control system. Attribution, copyright Rice University, OpenStax, under CC by 40 license. As part of requirements modeling, UML diagrams are drawn whenever they bring value to help provide a conceptual perspective of what the solution is meant to accomplish. They are generally not required to be complete or perfect. The use of UML in this manner is typically referred to as UML as sketch, and it involves informal and incomplete diagrams. Instead of drawing UML diagrams, it is possible to specify them via scripts to automate the creation of diagrams, which can save valuable time. As mentioned, the main goal of requirements analysis decomposition in the inception phase is to understand the problem, while the main goal of the elaboration phase, which comes next and involves software design, is to clarify what we are to implement. Elaboration framework activity. The elaboration phase further analyzes the requirements to produce design models of the system to be developed. In this phase, you take a deeper dive into the specifics of the software. Requirements are refined in detail. A detailed design is created that outlines the architecture of the software, and the potential risks associated with the project are identified and assessed. Design models are defined at a high level, initially, to represent the various facets of the architecture of the solution that is being developed at a given level of scope. The scope could be that of a whole enterprise, a portfolio of solutions contemplated by a business unit, or a specific solution being developed by a business unit as part of a given project. Architectural facets are typically based on architectural domains specified in mainstream architecture frameworks. For example, the Open Group Architecture Framework, TOGF, splits high-level architecture representations into 4 domains: business architecture, application architecture, data information knowledge wisdom architecture, and infrastructure architecture. Various high-level modeling languages and associated tools may be used to facilitate the creation of high-level architecture models, e.g. TOGAF's Archimate Certified Tools 4. The management of enterprise and solution architectures is described in more detail in Chapter 10, Enterprise and Solution Architectures Management of this book. A detailed-level design model may then be derived from the high-level architecture model, and it is typically represented using a combination of low-level modeling languages, e.g. BPMN, UML, SysML. At this level of design, a conceptual solution that fulfills the requirements is created and seeks to answer the question, how will the system fulfill the requirements? The conceptual solution leverages the inputs collected in the inception phase to design a software product. This information is generally organized into 2 types of design, logical and physical. Logical design ignores any physical aspects. For example, a cruise control system needs to keep track of the maximum speed selected and whether the cruise control system is on or off. This information is gathered as part of the logical design and needs to be captured via a diagram that also identifies the corresponding relationships. This type of information is often captured as a set of entities, or actors, that enable the grouping of descriptive information and attributes. A graphical representation of the method for effectively implementing what was determined in the logical design of a software solution is a physical design. It includes defining where information comes from and where it goes within the plan system. It includes defining how information is obtained, processed, and/or how it is presented. For example, the physical design for turning on or off the cruise control system within an automobile can include using controls made available to the driver on the steering wheel to turn on or off the cruise. There could also be controls via pressing the brake pedal to turn off the system. Work on the logical and physical designs is generally performed first as a high-level design software engineering action, followed by a detail-level design software engineering action. The focus of the high-level design, HLD, software engineering action is on providing a general description of the overall system design. and can include information on the overall aspects of a system, including its architecture, data, systems, services, and platforms, as well as the relationships among various modules and components. Its focus is to convert the requirements into a high-level representation of the solution that can then be further refined as part of detail-level design. The focus of the detail-level design, DLD, software engineering action, is to detail or expand upon the HLD. As part of the DLD, every element of a system is provided with detailed specifications, and the logic for each component within each module of a system solution is determined. DLD is then used to implement the actual solution as part of the construction phase of the software process. Some of the differences between HLD and DLD are: HLD gives high-level descriptions of functionality, whereas DLD gives details of the functional logic within each component of a system. HLD is created first, with DLD created as an extension of the HLD. HLD is based on the requirements of the software solution, whereas DLD is based on extending the HLD. DLD should, however, still align with the requirements. HLD provides elements such as data and information design, whereas DLD provides the information needed to create the actual programming specification and test plan for using the data. A solution architect is generally involved with the HLD. Programmers and designers are generally involved with DLD, software architecture work product. The software architecture work product acts as a blueprint of the solution being worked on. Imagine you're building a house. Before construction begins, you would create a blueprint that outlines the overall structure, major components, foundation, walls, roof, and how they fit together. This blueprint is similar to a software architecture. In software development, a software architecture provides a high-level overview of a software system. It describes the system's major components, their interrelationships, and how they work together. This high-level representation helps developers understand the overall design before delving into details. A solution is typically represented at various levels of abstraction. Software design involves using software architectures to represent solutions at a high level of abstraction. A software architecture constitutes a relatively small, intellectually graspable view of how a solution is structured and how its components work together. The goal of software architecture modeling is to allow the software engineer to view and evaluate the system as a whole before moving to component design. This step enables the software engineer to ensure that the design model encompasses the various solution requirements, make it possible to survey various design alternatives early on to facilitate the adoption of the best possible model, limit the risk of building software that does not meet the requirements. When you look at a blueprint, you can see the major elements of a building and their relationships to each other. When you look at a software system at a high level of abstraction, such as the extremely high level shown in Figure 9.7 of a web browser, you can see its major components and the main connections between them. For example, at a high level, a web browser connects to a web server via HTTP requests, and the web server interacts with a relational database via SQL queries to create an HTML web page that is rendered dynamically and sent back to the web browser for display. Graphics showing looping connection from web browser to HTTP to web server to SQL to database to web server and back to web browser. Figure 9.7. The software architecture displays a system's major components, in this case, web browser, web server and database and connections, HTTP requests and SQL queries at a high level of abstraction. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Software architecture is an important part of the creation of a software solution, and it should always be designed by an experienced software engineer because changes in the software architecture typically have drastic effects on the solution implementation, such as constructing solutions that do not meet the non-functional requirements. When designing software architecture, you can leverage various types of software patterns that facilitate the reuse of pre-existing solutions. Two examples of such patterns are an architectural style and architectural or design pattern. An architectural style is a transformation that is imposed on the design of an entire system. The intent is to establish a structure for all components of the system. Architectural or design patterns also impose a transformation on the design of an architecture, but they differ from a style because they operate at a lower level of abstraction. Patterns can be used in conjunction with an architectural style that shapes the overall structure of a system. A software architecture is one of the work products that results from the HLD software engineering action. Software architectures are important work products because they provide high-level representations of solutions that facilitate communication among all stakeholders. They also highlight early design decisions that have a profound impact on all software engineering work that follows. When it comes to agile software processes, the goal of creating software architecture work products as part of the HLD software engineering action is to avoid rework. In that case, user stories are leveraged to create and evolve an architectural model, sometimes referred to as a walking skeleton, before constructing the software. The use of agile software processes sometimes makes it difficult to manage architectural design, especially when the team is developing large systems from scratch, rather than adding small services piecemeal to an existing system. Agile approaches typically focus on small increments, for which it may be difficult to produce an all-encompassing architecture that will be able to accommodate subsequent increments that have not been completely defined yet. This may lead to having to refactor the architecture, which could be very costly, as it may require changing a lot of the code that has already been developed. Therefore, it is recommended that teams thoroughly consider architectural design when taking on large projects that do not build on an already defined and solid architecture. This brings up the question as to whether big design up front, BDUF, is the preferred method in this case. It is also the reason agile teams should include software engineers with a strong background in architecture, ideally, enterprise architecture, who can foresee the type of designs that are required to avoid costly refactoring efforts in the future. The Scrum and Kanban agile process models, as you'll learn later in the chapter, allow software architects to add user stories to the evolving storyboard and to work with the product owner to prioritize their architectural stories in work units called sprints. Well-run agile projects include the delivery of software architecture documentation during each sprint. After the sprint is complete, the architect reviews the working prototype for quality before the team presents it to the stakeholders in a formal sprint review. As mentioned earlier, the focus of the HLD software engineering action is on providing a general description of the overall system design. It can include information on the overall aspects of a system, including its architecture, data, systems, services, and platforms, as well as the relationships among various modules and components. Its focus is achieved by converting the requirements into a high-level solution that can then be further refined as part of the low-level design, LLD, software engineering action. Link to learning. The IEEE Computer Society has proposed IEEE STD 40 2010, 2022, Software, Systems, and Enterprise Architecture Description as a standard that describes the use of architecture viewpoints, architecture frameworks, and architecture description languages, ADLs, as a means of codifying the conventions and common practices for architectural description. Software design, the abstraction and refinement of requirements into a specification that can be used to help create a software solution, is referred to as software design. Software design is a software engineering task set that is part of the DLD software engineering action. The focus of the DLD software engineering action is to detail or extend the HLD work products. As part of the DLD software engineering action, every element of a system is provided with detailed specifications, and the logic of each component within each module of a solution is determined. Software design generally requires problem-solving skills, as well as the ability to conceptualize framing, as well as define it, into a working specification that can be used to create a software solution. In contrast to the HLD software engineering action, the LLD software design task set is concerned with all the implementation details. In agile approaches, we typically postpone many design decisions until implementation time and only design upfront the parts that are tricky or that need to be solved in an unusual way. The main concepts that drive software design are abstraction, high-level representation of components such as data or data objects, and procedures, the sequence of instructions that usually have specific and limited function. Architecture, overall structure or organization of software components, ways components interact, and structure of data used by components. Component-based software engineering, CBSE, can be considered as a task set as part of the DLD software engineering action to assemble solutions based on the reuse of pre-existing components. Design patterns, a design structure that solves a well-defined design problem within a specific context. Pattern-based design can be considered as a task set as part of the DLD software engineering action to assemble solutions using implementation patterns and frameworks. Separation of concerns. A technique based on the idea that any complex problem can be more easily handled if it is subdivided into pieces. Modularity, compartmentalization of data and function. Information hiding. Controlled interfaces that define and enforce access to component procedural detail and any local data structure used by the component. Functional independence. Single-minded, high-cohesion components with aversion to excessive interaction with other components, low coupling. Stepwise refinement, incremental elaboration of detail for all abstractions. Refactoring, a reorganization technique that simplifies the design without changing functionality. Design classes provide design detail that will enable analysis classes to be implemented. The work products generated as part of the DLD software engineering action are used to construct the actual solution. There are many other task sets that could be considered as part of the DLD, including prototype, user experience and user interface design, and specific design task sets for web, mobile, social, and gaming solutions design. Think it through. Asking the right questions. In 1998, the Mars Climate Orbiter was launched toward Mars to study its climate. Unfortunately, the lander was never able to complete its task. The probe ended up being destroyed by the Martian atmosphere due to an error in the mathematical calculations. However, the issue was not with the calculations, but the numbering system that was used for distance measurements. The software in the probe used the metric system, but the team from Earth that sent the data to the probe sent their values in imperial numbers. The result was a destroyed probe. Was this a design error? What could have been done to avoid a mistake, such as using the wrong measurement system? Construction framework activity. As part of the construction phase or framework activity, the design documents that result from the DLD software engineering action of the elaboration framework activity are used to write corresponding source code in a programming language, as well as create any supporting assets such as deployable container images, databases, and controls. This is where the coding magic happens. Developers work to build the software based on the design created earlier. This phase involves writing code, testing individual components, and fixing defects bugs. Source code may also be automatically generated from design work products using round-trip engineering tools, although this type of functionality is still limited today. The development methodology model-driven engineering, which is compatible with agile methods, stresses the importance of formal and executable specifications of object models and the ability to verify the correctness and completeness of the solution by executing the models. This is typically made possible when using round-trip design engineering tools and frameworks that allow for the specification of models using standard modeling notations and the creation of evolvable software from these models. E.g. JBPM5. The result of the construction phase is a complete running solution that is based on the design work products and meets the expectations set forth as part of the inception phase. It should be noted that coding is a mechanistic outgrowth of procedural design, and errors can be introduced as the DLD design work products are translated into a programming language. This is particularly true if the programming language does not directly support data and control structures represented in the design. Code walkthroughs are designed to avoid this. The field of DevOps, a wide-ranging collection of development and operations practices, has introduced further processes and infrastructure to automate many of the software engineering actions that are part of the construction phase. When these methodologies have been applied together, agile methodologies and DevOps, automation have increased the speed, robustness, and scalability with which software can be constructed. Software engineers use many tools to implement solutions. These include code editors such as Atom, integrated development environments, IDEs such as VS Code or Visual Studio, version control systems such as Git, debugging tools, testing tools, and more. Link to learning. Which programming language to learn often depends upon the type of programming that needs to be done or what a business currently uses. While there is no perfect way to determine which programming language is used the most, the TOB index gives a general idea of which languages are most popular. This index is updated monthly and provides an indication of the changing popularity of programming languages. The rankings are based on factors including the frequency of searching on related topics, courses taught, and more. Of course, each programming language has strengths and weaknesses, so when choosing which language to learn, sometimes it's best to focus on the context of the solution you need to create and not just popularity. Unit integration and system testing. Unit integration and system testing deal with ensuring and verifying that the software system works as expected. It typically involves activities to uncover errors that were made inadvertently during the elaboration and construction phases. Code reviews and unit integration and system testing are typically done as part of the construction phase by software developers responsible for writing source code. The process whereby the source code written by one developer is manually inspected by another developer is called code review. This is especially useful when the software team consists of developers with different levels of experience. It is worth noting that while SDLCs often include testing task sets within specific phases, testing is an activity that should happen repeatedly throughout the software process independently from the actual phase or iteration of such that is currently being executed. Deployment framework activity. Deployment is the phase that makes software available to users. Finally, the software is released to the users. This phase involves delivering the software to its intended audience, e.g., launching a mobile app on an app store and providing ongoing support to address any bugs or issues that arise after deployment. In the past, deployment often meant installing the software on a customer's computer. Today, software is more likely to be installed on special computers or powerful online systems called cloud servers. When deploying software, some configuration might be needed, especially for complex applications. DevOps uses automation to make deployment faster and more reliable. Modern software is often updated frequently using special tools and techniques. As noted, deployment, especially if it is a non-trivial task that is not expected to be done by the customer, typically involves configuring the software solution. In a typical configuration process, the software solution is containerized or packaged in such a way that it can run on different computer systems easily, and then deployed via a system called Kubernetes clusters that automatically manages scalability and availability. The field of DevOps has introduced additional processes and infrastructure to automate many of the software engineering actions that are part of the deployment phase. Together, agile methodologies and DevOps automation have increased the speed, robustness, and scalability with which software can be deployed today. It is worth noting that modern applications deployment techniques have evolved quite a bit as a result of DevOps automation. Software updates are deployed frequently today using continuous integration and deployment (CI/CD) techniques and tools. Maintenance. Most deployed software will eventually need updating to add new requirements or fix issues that might arise. The process of updating software after it is deployed is referred to as maintenance. As mentioned earlier, maintenance is a software engineering action that is part of the software process deployment phase. The cost of maintenance can exceed that of development, especially if software remains in use for a long period of time. You may think of the process of creating software as being analogous to that of building a new car. Maintaining the software is like maintaining the car while you use it. To make the analogy more precise, while software does not wear out like car hardware might, its maintenance involves updates to fix bugs and adding new features as requirements change. Building a new car may take several weeks, but car maintenance will probably last much longer because the car may be used for years. As for expenses, building a new car will cost a significant amount, but costs related to its maintenance will easily exceed the price of the car when it was new. Of course, when the costs of maintaining a car become too high, there is always the option of buying a new car, just as there is the option to build a new software product if maintenance of the legacy software gets too high. In agile process models, a lot of the maintenance is not limited to adding new features. Instead, it often involves the following: using Scrum sprints to plan the work and address customer needs without overwhelming developers, giving priority to urgent customer requests, and allowing corresponding interruptions of planned maintenance sprints to address these urgent requests, making it possible for team members to prioritize the handling of customer requests and coordinate their processing as part of the maintenance process, combining the use of meetings and written documentation to minimize the duration and frequency of meetings and keep them focused, relying on informal use cases when communicating with stakeholders to supplement existing documentations and keep communication simple, requiring that developers verify each other's work. In particular, experienced developers should review the work produced by junior developers, such as defect fixes or code added to support new features. to help them develop their knowledge. Cross-cutting umbrella activities. In addition to the core process framework activities, namely inception, elaboration, construction, and deployment, there are many activities that can take place at any point during the creation of a solution and throughout the entire software process. In other words, they cross-cut the process. To understand the importance of such activities, consider this analogy. In addition to completing the main stages of building a house, e.g., constructing the foundation, walls, roof, there are other important activities that happen throughout the project, e.g., choosing the colors of wall paint. These are like the umbrella you would use on a rainy day. They support the entire process, but aren't part of the main building steps themselves. In software development, a cross-cutting activity, or an umbrella activity, is an activity that cross-cuts the entire software development process, but is not part of the main building steps themselves. They can include communication and training, risk management and planning, software configuration content management, quality management, architecture management, and software security engineering. Communication and training. Establishing communication involves scheduling regular meetings between developers and customers, and also meeting with developers to train them on new technologies. It is necessary to communicate with stakeholders and customers at various points in the software development process. For example, collecting project requirements during the inception phase involves communication and coordination between project managers and stakeholders. Release notes serve as another form of communication, and they are written for software users to make them aware of the features that are included in a new release. More generally, the status of a project needs to be communicated with management at regular intervals to make sure that satisfactory milestones are reached according to plan. Regular communication also happens within software development teams. For example, design reviews encourage communication to help finalize designs. Code reviews focus on communicating how the system is changing and how to solve problems and improve code. Daily stand-ups in agile software processes are about concise verbal communication. Software engineering team members must undergo training on a regular basis to acquire or maintain certain skills. To support this, software development teams typically put in place organizational change transformation methodologies and frameworks, e.g., prescribe three-phase process, to manage their ability to successfully conduct projects given the changing nature of software engineering. Risk management and planning. Risk management and planning focuses on identifying potential risks like project delays and having a plan for how to address them. Software development is a complex activity that involves many people working over a long period of time, and it turns out that not every project succeeds. Some projects are delayed, some of them overrun the budget, and some are never finished. The high percentage of unsuccessful projects creates a need for risk management and mitigation. Minimizing risk is typically the main task of a manager, but software engineers can also take on management tasks. For example, to help managers, they might provide updates that allow managers to refine their risk assessments. Ideally, these updates would address the different components of risk, including performance risk. Considers whether the product will not fit its intended use. Cost risk determines if the budget constraints can be maintained. Support risk assesses how easy the product will be to maintain and update once it is completed. Schedule risk considers whether the project will meet expected deadlines. Risk projection attempts to associate with each risk the likelihood of its occurrence and the consequences of the resulting problems if a risk should occur. One of the software process models you will learn more about later in this chapter is called the unified process. In this process, risks are mitigated by selecting risky requirements for early iterations. For example, a use case that requires a new technology is typically considered risky, as well as a use case that assumes integration with legacy code. We select such use cases for an early iteration because if their implementation happens to fail, it is better to fail in the beginning of the project rather than in the end. As the project continues, managers focus on minimizing risk across the 4Ps: the people involved, the product being developed, the process being followed, and the project work being completed. While the agile and traditional software processes use different approaches, the goals for each are the same: controlling risk by providing people with a well-defined product and clear processes to follow. These goals allow software engineers to estimate the work required and track the product through development. Managers compare the product completed against those estimates and use those results to make any needed adjustments. Technology in everyday life. Delivering viable systems. The development of software often focuses on three areas: desirability, capability, and viability. In other words, the focus is on what is wanted, what is possible, and what will sell or help a business to function. To be successful, a software product must deliver something people want and is of value. It must also be possible to implement the product. In the 1980s, the first virtual reality software was released. VR was something that many people wanted and saw a value in having. However, the technology was not capable of delivering a viable system. It is only today that software and hardware capabilities can support VR at a level that makes it possible to deliver products that people are willing to pay for. What are some other technology areas that are viable today that were not viable 10 years ago? What are some software technologies that are not viable today that could be viable within the next 10 years? Software configuration and content management. Software configuration management, SCM, is a cross-cutting activity that helps report, identify, and control change to items that are under managed development. These items are referred to as software configuration items, SCIs. SCM also analyzes the implementation of change and provides mechanisms to publish and deploy change. One way to reinforce the importance of configuration management without a real customer is to change the project requirements sometime after the project implementation begins. The focus of SCM tends to be on four main areas: configuration identification, the identification of all components within a project, including any files, documents, source code files, directory structures, and more. Configuration change controls, the controlling of who accesses elements of a project and the tracking of changes being made. Configuration status accounting, the tracking of who made a change as well as when they made the change and why it was made. Configuration auditing, the tracking of the status of a project, and more important, the tracking and confirmation that what is being created matches what is required. Many Agile teams make use of continuous integration to ensure that they always have viable prototypes ready to test and extend. The advantages of continuous integration are as follows. Involves frequent feedback to notify developers promptly when integration testing fails so they can fix issues as quickly as possible, especially if the number of fixes required is small. Improves quality by being able to address product changes quickly. As a result, users can trust that the product meets their needs. Reduces risk by avoiding long delays between the time software is developed and its integration into the product. This ensures that design failures can be detected and addressed early on. Involves up-to-date reporting to ensure that software is correctly configured to conform, for example, to the latest code analysis metrics. Ensures that streamlined integration is used as key support technologies in organizations that use Agile software process models. Captures defects as early as possible in the software engineering process, which limits the cost of software development. Various tools may be used to support SCM, including audit management tools, e.g. ZenHub configuration management automation tools, e.g. Ansible Vagrant, continuous integration tools, e.g. Jenkins, Travis CI, dependency tracking and change management tools, e.g. Basecamp Jira, source control management tools, e.g. GitHub, and so on. Content management includes collection, management, and publishing subsystems. The collection subsystem facilitates the creation and acquisition of new content. It also makes it possible for humans to relate to the content and combines it as units that can be displayed more effectively on the client side. The management subsystem provides a repository for content storage capabilities, including the content database, i.e., the information structure used to organize all the content objects, the database capabilities, e.g. functions to search for content objects, store and retrieve objects, and manage the content file structure, and configuration management functions, e.g. supports content object identification, version control, change management, change auditing, and reporting. The publishing subsystem extracts content from the repository, converts it to a publishable form, and formats it so that it can be displayed in a web browser, e.g. Chrome, Safari. The publishing subsystem uses a series of templates for each type, including static elements, e.g. text, graphics, media, and scripts that require no further processing are transmitted directly to the client side. Publication services, i.e. function calls to specific retrieval and formatting services that personalize content, perform data conversion, and build appropriate navigation links, and external services that provide access to external corporate information infrastructure, such as enterprise data or backroom applications. Software quality management. Whereas testing validates that things work as expected and that there are no errors or issues, software quality management, SQM, focuses on the development and management of the quality of the solution being developed. Tasks within SQM involve quality planning and quality control. They include, but are not limited to, activities such as confirming requirements are correct, complete, and consistent, verifying that all elements of design conform to the requirements and are of high quality, confirming that source code follows coding standards and is written in a manner that will be maintainable going forward, ensuring that testing checks all elements of a solution, implementing a change management plan. Engineering quality software subsumes a deep understanding of the solution requirements and the ability to design work products that conform to these requirements. These activities must rely on the use of software engineering best practices and must be supported by adequate project management. Assessment reviews, e.g., system engineering assessments, software project planning assessments, analysis models assessments, design models assessments, source code assessments, software testing assessments, and maintenance assessments, are an important quality assurance mechanism. Software quality assurance, SQA, is part of a broad spectrum of software quality management activities that focus on techniques for achieving and/or ensuring high-quality software. Architecture management. Returning to the analogy of how software architecture is like the blueprint of a house, software architecture management can then be likened to improving the blueprint as you use it to build the house. To put it another way, creating the blueprint architecture was just the first step. In software development, architecture management involves keeping track of the blueprint and making sure it stays up to date as the software is being built. This helps avoid problems later on. While HLD is a software engineering action that takes place in the software process elaboration phase, the architecture management umbrella activity encompasses a set of architecture management and architectural refinements techniques that can help improve the architectural design while it is under development. Architecture management efforts may be performed at any point within the software lifecycle, which explains why architecture management is a good umbrella activity. It maintains the knowledge required to qualify the goodness of solutions from a design standpoint, and it is handled separately from the quality management umbrella activity. There are special tools that can help with architecture management. Similar to using software to draw up the blueprint of a house, these tools can help store and organize the architecture information and make it easier for everyone working on the project to understand it. Examples of such tools include artifact package management tools, e.g., Docker Hub 6, JFrog Artifactory 7, and pattern catalogs. Software security engineering. Engineering software security focuses on protecting software assets against threats. Threats typically exploit software vulnerabilities to compromise the confidentiality and integrity of data. Threats may also compromise the availability of software systems by disrupting access to system services and related data. Software architectures must be designed to address security requirements and eliminate vulnerabilities that can lead to exploits. Various design techniques can be used by software engineers to address the possibility and the effects of attacks in order to minimize related losses and costs. As an example, Microsoft's Square process model provides a means of eliciting, categorizing, and prioritizing security requirements engineering for software-intensive systems. Keeping up with cybersecurity threats is proving to be difficult for businesses these days due to a lack of trained resources and increased demand for security compliance. Traditional approaches to security are no longer viable to ensure that organizations can keep operating as well as develop competitive solutions. For that reason, many businesses are combining traditional software process models or agile process models with modern approaches, such as DevSecOps, to manage software security engineering. Using DevSecOps requires the adoption of new processes and tools as well as the training of staff members. The DevSecOps approach automates the support of security throughout the SDLC, which reduces time and costs of development and facilitates the integration of the security and development teams. Some examples of DevOps security tools are Aqua Security and HashiCorp Vault, and examples of DevSecOps tools are Sonar Quebec and Zebia Labs. Popular software process models. The framework activities, or phases, that have been presented as part of the process framework are general phases that get applied within software process models, SDLCs. The types of software engineering actions that get applied with each phase depend on the software development model that is used for the project at hand. There is a multitude of SDLC models. These models have evolved over time and offer various approaches to creating software solutions. Some more traditional SDLCs are prescriptive in terms of the software engineering actions that must be conducted, while others are agile. Agility, as you know by now, has to do with the ability to skip some software engineering actions or make some of the deliverables optional in order to meet deadlines and still deliver a quality product within budget constraints. As you may recall from Figure 9.4, there is a spectrum of agility between software process models. By nature, SDLCs are incremental, as it is always possible to consider a subset of requirements for a given release. In fact, there are typically as many increments as there are subsets of requirements. To accommodate changes in requirements and possibly new requirements within an increment, SDLCs can involve iterations that make it possible to add to and replan increments on an ongoing basis. This adding and replanning may introduce backlogs because usually the original timeline cannot be changed. In short, SDLCs can be made agile, incremental, and iterative. Historically, traditional models were incremental but not iterative or agile. The Unified Process (UP) model was the first traditional model to introduce iteration, and it was quite prescriptive and therefore not agile in terms of expected deliverables. Agile software process models are always incremental and iterative. That said, it does not make sense to use an agile software model if the requirements are known and not expected to change during the increment. In that case, using out-of-the-box solutions may, with the help of some collaborative features found in Agile process guidelines set forth in Agile ASDE's SDLCs, produce better results. Traditional software process models follow a step-by-step plan, akin to building a house according to a blueprint. They are good for projects with clear requirements that don't change much. While some organizations define the software development model their software engineers are expected to use, it is almost often better for teams to pick or tailor a software process model so it aligns with the project at hand. Some of the popular software process models include waterfall model, V model, incremental model, prototyping model, spiral model, unified process (UP) model, agile process models. Waterfall, predominantly used in the early days of software engineering, the waterfall model is a continuous prescriptive software process model in which phases flow into another the way water flows from the top of a waterfall down to the bottom. In the waterfall model, the requirements are first gathered and analyzed, then a complete software system is designed, the system is implemented, and then final testing is done before the system is finally deployed. Unfortunately, the traditional waterfall model did not make a distinction between phases and software engineering actions, and therefore, the steps it uses correspond to specific software engineering actions or task sets with custom names that should be conducted in a prescribed sequence. Our generic process framework may still be used to represent the waterfall process, but framework activities would have to be ignored and specific software engineering actions or task sets that correspond to the waterfall phase names would have to be used. For example, some of the testing task sets from the SQA software engineering action of the quality management umbrella activity could be pulled together to make up the waterfall testing phase. In the waterfall model, software engineering actions or task sets are performed in a strict order as shown in Figure 9.8, and each one of these has a required output in the form of artifacts, such as a document, diagram, or code. This software process is not agile, so it is not possible to skip a step or drop a deliverable. For example, the output of requirements analysis is a document that describes all requirements for the system. Because this process is not iterative, it is not possible to go back to a previous step to modify this output. For example, if the final design document contains a mistake, it could not be revised during the implementation step. The next step would be testing. Note, however, that there is nothing that keeps the waterfall model from being used incrementally. The concept of incremental development was simply not understood when waterfall was first used. Waterfall chart. Requirements to design to implementation to testing to deployment. Figure 9.8 in the waterfall model, one step of the software development process flows into another, and each is required to produce an output in the form of a document, diagram, or code. Attribution, copyright Rice University, OpenStax, under CC by 4.0 license. The major advantages of the waterfall model include: it is easy to understand and use. Steps and corresponding software engineering actions or task sets are conducted sequentially. The artifacts are well documented. Although the waterfall model has some advantages, they are often outweighed by its disadvantages. It cannot easily accommodate changes in requirements. If there is a change in requirements, it is necessary to go back to the first step of the process model and update all the artifacts that were previously completed. No software product is provided until late in the life cycle. Because software is not available until the end of the implementation construction step, it is not possible to ask the customer for feedback during the process. It produces many artifacts, which are not always necessary. Therefore, a lot of time may be spent creating unnecessary artifacts. Despite these disadvantages, the waterfall method is useful in situations where requirements do not change and interaction with the users of a system is limited or non-existent during a project. The V model. The V model for software development is also known as the verification and validation model. The V model is similar to the waterfall model in that it is a continuous prescriptive model that includes basic initial system creation, steps starting with gathering requirements, designing the system, and coding it. Each step is prescriptive and conducted sequentially. Where the model differs is that each step of the V model is associated with a verification or validation testing step phase, as shown in Figure 9. This testing is planned in coordination with each of the design and implementation steps phases. Like the waterfall model, the V model is considered easy to understand and use because it follows a specific flow when it comes to steps phases, and each step phase is only completed once. Also, it is best suited for smaller projects where the requirements are easy to understand and unlikely to change after the project starts. The V model's advantage over the waterfall method is that verification and validation testing is more integrated into the overall process. The V model, however, does have several disadvantages, including it is not good for larger, longer projects or projects that may involve changing requirements. A usable software product will not be available until near the end of the software development lifecycle. Once testing is started, it becomes more difficult to make changes to the design. V-model verification, requirement analysis, system analysis, architecture design, module design, coding, validation, unit testing, integration testing, system testing, acceptable testing. Validation is shown from all validation steps back to verification steps. Figure 9. The V model is like the waterfall model in that it is also a continuous prescriptive software process model. Despite their visual differences in both models, each step is conducted sequentially. Attribution. Copyright Rice University, OpenStax under CC by 4.0 license. Incremental model. In the incremental model, the software process is divided into modules. Each module focuses on a smaller set of requirements based on an overall business plan. These smaller sets of requirements are then used to design, implement, and test that part of the software solution, as shown in Figure 9.10. Once all the modules are completed, the software solution is deployed to the users. Note that increments in this case are different from iterations. It is assumed that each increment focuses on a small subset of requirements, and it is not possible to accommodate possible changes to requirements. Projects are typically split into a number of increments meant to cover customers' needs over a period of time that is acceptable to them, while each increment is made manageable by the development team. Illustration of increment model with overall requirements split into different increments, each consisting of requirements, design, implementation, testing, deployment, and resulting in overall deployment. Figure 9.10 in the incremental model, the software process is divided into increments or modules, and each module focuses on a smaller set of requirements based on an overall business plan. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The incremental model is best suited when the requirements are clearly stated at the start of the project, and the product needs to be released quickly. Because the increments are small, testing can be done, and user feedback can be gained with each increment. This means there are opportunities to identify and fix errors or issues with the product sooner than in the waterfall or V-model methods. Once the overall requirement step is complete, each increment can focus on its specific delivery. This helps to reduce costs, especially if there is a change in the requirements. Additionally, a big advantage of the incremental model is that it is easy to know how much has been completed and what remains to be done. Prototyping model. The prototyping model requires the quick creation of a mock-up or demo of the expected final product that does what the final product is expected to do in order to be able to show end users what the system could look like and how it might function. Because the users can see what the product may look like and the basics of how it may function, they are in a better position to provide feedback that can be incorporated into the demo and then built into the final product. The prototyping model is also known as a RAD, Rapid Application Development, model because its focus is on getting a working demo created rapidly. This model still uses gathering requirements, designing, implementing, and testing steps. However, they are all done quickly to build the prototype. The focus is on improving the prototype to get to what is required to build the final software solution. As shown in Figure 911, the prototyping model can be used to build a mockup that the user can approve, and then the mockup can be used as an input to the standard process of designing, implementing, testing, and deploying the actual product. Prototype model, gather requirements, quick design, implement prototype, user review of prototype, changes requested, update requirements with user feedback, accepted, design final product, implement code final product, test final product, deploy final product. Figure 9.11, a prototyping model focuses on the quick creation of a mockup or demo of the final product that can be shared with users to gain their feedback. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The prototyping model has some drawbacks. Because it involves getting the user involved early, the process of testing and incorporating feedback can become time-consuming. Additionally, while the prototype might appear to work, generally it will lack the full internal functionality, which must still be built even after the user sees what appears to be a working system. This may require added effort to be made to manage expectations about the final product. Spiral model. The spiral model is a combination of the waterfall model with an iterative model approach and a focus on reducing risk within a project. As with the waterfall model, the spiral model starts with requirements gathering, except that it starts with a small set of requirements and then cycles through planning, design, implementation, and testing for those requirements. After the initial set of requirements is addressed, the process iterates back to the beginning, where additional requirements are applied to the project, and then it continues cycling, as illustrated in Figure 9.12, until the software solution is ready for deployment. This model differs from the waterfall method in that it includes a risk analysis as part of the planning step. The risks associated with the project are also assessed during the review and testing of the system. Spiral model illustration. 1. Determine product objectives and identify solution options. 2. Assess, identify, and resolve risks. 3. Develop and test the current product iteration. 4. Plan the next product iteration. Figure 9.12. The spiral model prioritizes risk analysis by combining elements of the waterfall method with an iterative approach. Each spiral addresses a small set of requirements, but cycles through planning, design, implementation, and testing stages for those requirements. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The spiral model is often used on larger projects or when frequent releases are expected. It is also used when risks are considered high for a project and need to be monitored closely. Such risks can include cost, unclear requirements, complex requirements, or having requirements that could change. The advantage is that because of the spiraling, iterative nature of the model, changes can be added later in the project. Additionally, the model allows for better estimation of costs for individual iterations because a limited number of requirements are being addressed during each spiral. Because each iteration allows for the system to build upon itself, there is also the benefit of being able to adapt to user feedback and changing requirements. The spiral model does have its disadvantages. Because there is an added focus on risk, it requires expertise in risk management. Additionally, the iterations not only add new features, but can build upon existing features, which can lead to added costs. If applied to smaller projects, the cost can outweigh the benefits of some of the other approaches. Because there are multiple iterations composed of several steps phases, it is also important to follow the processes more strictly than in the case of other models, and keep good documentation to know what has been done and what is expected. Unified Process Model. In the Unified Process (UP) model, the development of a software system is divided into 4 primary phases: inception, elaboration, construction, and transition, each of which involves multiple iterations that include the standard software development processes, as shown in Figure 9.13. Like the framework activity phase in our generic process framework, the UP model differentiates phases from software engineering actions. The UP model still relies on a continuous prescriptive process, but it supports incremental iterative development. The UP model uses the word discipline or process to refer to the software engineering action defined in our process framework. The names of the phases are almost the same as the names of the phases in our process framework, although the transition phase is equivalent to deployment in our process framework. Unified process chart listing inception, elaboration, construction, and transition with iterations for business case development, requirements gathering, solution design, implementation, testing, and deployment. Figure 9. 13. The unified process model is very similar to the generic process framework, as it includes phases in the form of processes, or disciplines. It also features iterations, and the relative size of the colored area for a given discipline indicates how much of the discipline is performed in each iteration. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Each phase or process of the unified process model has its own goal. In the inception phase, the goal is to get the users to buy into the solution being presented, document the requirements, and create an initial plan for the project. The elaboration phase focuses on the solution design and firming up the project plan. The construction phase focuses on implementing and testing the software. Finally, the transition phase focuses on the deployment of the solution. As in other traditional process models and in contrast to the Agile models, each phase of the UP model results in a set of deliverables. In the inception phase, this might include documents like a scope statement, initial risk assessment, or preliminary project plan. In the elaboration phase, a software development plan, revised business case, or executable architecture baseline. In the construction phase, individual iteration plans, release description document, or user documentation. And in the transition phase, final product release and lessons learned analysis, among others. Note that the amount of time spent in each discipline changes over time, so that as the project evolves, less time is spent on requirements and design, and more time is spent on testing and deploying. The expectation is that the model adjusts the extent of software engineering actions on an ongoing basis, depending on what is needed to develop the software solution at a given time. The expectation when using the UP model is that software will be delivered early and regularly throughout the process. Additionally, the model allows users to see what is coming and provide feedback, which, in turn, allows the software to be adapted to any changing needs. This requires open communication throughout the process and keeping the users as active participants in the project. Another practice with this model is to focus on reusing existing code as well as on using modeling and other tools. Tools such as UML are almost always used as part of UP. Additionally, UP lowers risk through the iterative nature of the development. Because the iterations are time-boxed, there is better control of the overall process. This helps make risk easier to manage. The disadvantage is that the phases are combined with the disciplines and time and boxed into a set of iterations, which can result in a model that is complex to follow. To be effective, the disciplines need to be managed, and communication needs to be clear. It generally requires good management of the process. It is worth noting that UP was the first model that distinguished phases from disciplines, which made it possible to introduce iterations and integrate them with increments. While incremental development had existed before, the separation of phases from disciplines made it newly possible to plan iteration as part of a project increment and thus to create solutions more effectively, as software process actions were no longer associated to a specific framework activity phase. During each iteration, partial functionality could be created, and the results could be integrated with the rest of the system. Agile process models. Several popular software process models in use today align with the Agile guidelines. While the phases used within Agile process models are similar to that of other models, the difference is that some disciplines in various phases may overlap. For example, in the Agile process model, all the requirements do not need to be defined in the inception phase prior to starting the design or to coding disciplines in the elaboration and construction phases. New requirements or changes in requirements can be considered as part of subsequent phases. Additionally, an incremental, iterative approach is applied so that it is not necessary for all the functionality in one increment to be dealt with at once. It is worth noting that the incremental model that was presented earlier may be Agile for a similar reason. The benefits of Agile process models are they are flexible, i.e., allow for changes along the way and emphasize collaboration. They also allow for continuous improvement, which is advantageous if requirements are likely to change or needs are likely to evolve. The drawbacks are that Agile models can be difficult to scale. Agile principles. Agile principles were formulated in the Agile Manifesto that was a response to the unsatisfying number of projects that were delayed, overrun their budget, and did not meet customers' expectations. Agility refers to the ability to create and respond to change in order to profit in a turbulent business environment. Some Agile principles are as follows: satisfy the customer through early and continuous delivery of software. Welcome changing requirements, even late in development. Deliver working software frequently, such as each couple of weeks. The most effective way of communication within a development team is face-to-face, via collaboration tools. Working software is the primary measure of progress. Maintain a sustainable working pace. Continuous attention to technical excellence and good design enhances agility. Simplicity, the art of maximizing the amount of work not done, is essential. The best architectures, requirements, and designs emerge from self-organizing teams. The approaches that complement Agile software development are Scrum, DevOps, and Site Reliability Engineering. Link to learning. To learn more about Agile, you can visit the Agile Alliance to learn the core principles of Agile development from the experts. The Agile Alliance is a global nonprofit organization that is focused on applying and expanding Agile values, principles, and practices. You can view its tutorial What is Agile online, which provides more details on Agile and its use. Scrum. Scrum is a type of Agile software development model. The fundamental unit of Scrum is a Scrum team, which is typically 10 or fewer people. It consists of one Scrum Master, one product owner, and several developers. The Scrum Master is responsible for running Scrum and for helping everyone understand its theory and practice. The product owner is responsible for product backlog management, which includes product goals and product backlog items. The product goal describes future desired features of the product, and the product backlog item defines what is required to be added to the product. The product is developed in iterations called a sprint, which is a fixed-length event typically of 1 to 4 weeks. Each sprint starts with sprint planning, in which the team selects the product goals and product backlog items that will be implemented in that sprint. The selected product goals and product backlog items are moved to the sprint backlog, which is a plan for the current sprint. During the sprint, developers have a daily scrum, which is a 15-minute event for the developers that is held every day at the same time and the same place. During the daily scrum, the developers inspect the progress, and if needed, they adapt the objectives of the sprint. At the end of sprint, there is a sprint review, during which the Scrum team and stakeholders review a demonstration of what was achieved as part of the sprint increment, and the Scrum team gets feedback. After that, in the sprint retrospective, the Scrum team discusses what worked well and what worked poorly process-wise during the last sprint to produce the product increment and proposes changes to increase effectiveness. Figure 9.14 depicts the Scrum process. Sprint framework, product backlog to backlog refinement to sprint planning to sprint backlog to Scrum team, sprint daily Scrum to increment to sprint review, back to sprint retrospective product backlog or product backlog. Figure 9.14 The Scrum framework is organized around sprints, workflow events that involve intensive planning, daily collaboration, review, and retrospection. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The benefits of the Scrum framework include better quality of the product, decreased time to market, higher customer satisfaction, and increased collaboration within the development team. The drawbacks are that the approach requires training, it is not suitable for large teams, and it requires daily meetings. Link to learning. Atlassian, a worldwide company that creates team and project-related products, has a no-nonsense guide to Agile development that provides additional details on what Agile is as well as on related topics, such as Scrum, Kanban, Agile Project, the Agile Manifesto, and much more. Its site has a tutorial for Scrum as well as related articles where you can learn more about how to use Scrum in a project. DevOps. A DevOps model combines practices of software development and operations. It uses a short development lifecycle and continuous delivery to achieve high-quality software products. In a DevOps model, development and operations teams are merged into a single team, and software engineers participate in all parts of the software lifecycle. As shown in Figure 9.15, this lifecycle includes planning, design, development, testing, deployment, and operations in a continuous cycle. Figure 8 graphic. Left loop is DEV, plan, design, code, build, test. Right loop is ops, deploy, operate, monitor, feedback. Figure 9. 15 DevOps is an agile software process model that combines the practices of software development and operations such that software engineers participate in all parts of the software lifecycle. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Because the DevOps model involves a focus on both development and operations, there is less chance of errors or vulnerabilities existing in a released software product. This uniting of development and operations can also lead to faster releases or shipments of products. Because of the collaboration, there tends to be improved effectiveness, faster delivery, and an optimizing of processes. Where the DevOps process model can struggle is with systems that are complex as well as with legacy systems. The DevOps model requires strong teamwork and collaboration, or it will likely fail. Additionally, it requires that the team members have the right expertise to satisfy the expectations of the project, including the ability to do continuous integration and development. Link to learning. Some of the best practices associated with the fascinating field of DevOps include continuous integration, continuous delivery, microservices, infrastructure as code, monitoring and logging, communication and collaboration, among others. Read this perspective on what DevOps is and consider researching other opinions to find other perspectives to help fully understand the concept. Site Reliability Engineering. Site Reliability Engineering, SRE, is an approach that focuses on achieving appropriate levels of reliability when developing solutions. SRE was created to address the complexity of challenges created when software solutions get larger. It is important to make sure that software meets business needs while operating reliably. The ability to scale up must be balanced with the complexity of a solution while maintaining reliability within a system. In many ways, this is a similar goal to that of the DevOps. Three key parts of SRE are reliability, appropriateness, and sustainability. A system needs to be reliable to serve the needs of the client. The level of reliability needs to be appropriate. Specifically, some systems don't need 100% reliability 100% of the time. For example, a feature such as cruise control only needs to be reliable when it is in use. Additionally, most cruise control features do not need to maintain an exact speed, but rather can have a difference of a few miles or kilometers when the car is going up or down hills and be okay. Regarding sustainability, a system has to be sustainable and maintainable by people. As noted earlier, SRE is similar to DevOps in that both bring software engineering and software operations closer. However, DevOps tends to focus on the product solution, or the what, whereas SRE focuses more on how, i.e., how the solution will get done in a reliable and sustainable manner. Both focus on providing opportunities for collaboration across an organization to deliver solutions that will be successful for the client. Table 9.1 indicates areas where SRE and DevOps differ. SRE DevOps. Primary focus of reliability of a solution, primary focus of effective development and delivery of a solution. Focus on regulating it with specific measurements such as following service level indicators, SLIs, and service level objectives, SLOs. Focus on continual integration, CI, and continual development, CD. Prioritizes user experience by ensuring services run reliably, and meet slows works to use broad ideas, and does not specify how operations of services are run. Intended to be a role more than a framework. Although it can be performed by those outside of the specific role, although it can be a role. It is intended to be a philosophy adopted across a team. Works to move quickly to reduce cost of failure, works to implement gradual change to reduce the chance of failure. Works to have specific expectations of what is acceptable regarding failure or issues with new releases, accepts failure as a learning opportunity, and prioritizes rapid recovery and continual improvement. Uses automation and monitoring tools to standardize processes and reduce manual effort, works to reduce organizational isolation by working closer together, but does not necessarily go to the same level of using similar tools and techniques. Table 9. One comparison of SRE and DevOps. Suggested process model. Which process model is the best? There is no best process model, and no process model will work for every project or group of people. Each model has advantages and disadvantages to be considered. The recommended approach is to use the model that can be tailored best to fit the current project and the skills of the team members. Many organizations have already made this determination, and will have their own internal guidance on which model should be used. Regardless, it is often important to consider software process improvement, which is the process of transforming the existing approach to software development into something that is more focused, more repeatable, more reliable, in terms of the quality of the product produced and the timeliness of delivery, and more cost-effective. As shown in Figure 9.16, software process improvement typically involves 4 steps. Software process, from planning of improvements to implementation of improvements to evaluation of improvement to evaluation of the current situation and back to planning of improvements. Figure 9.16 software process improvement can be used to transform any chosen software process model into one that is more focused, repeatable, reliable, and cost-effective. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Industry Spotlight. Applying the right process. The proper selection and application of a software engineering process are important in every industry today, as these processes help ensure the success of the software solutions being developed. Software engineering offers many industries opportunities for improvement. For example, the New York Stock Exchange, NYSE, has engineered its software to offer stock trading capabilities to anyone anywhere so that they can trade at almost any time. As you can imagine, the NYSE software is complex, and any software issues encountered during trading hours can generate financial losses or cause reputational damages. These are some of the considerations that must have gone into the decision about which software engineering process to use to complete this upgrade. Of all the processes you've learned about so far, which one, do you think might be best for a project that involves developing a software solution to serve the global markets industry? Think about the possible ramifications of software development delays when addressing a software issue on a trading floor. Imagine a software defect causes stock prices to display incorrectly during peak trading hours. How could this impact the market and investors? Learning objectives. By the end of this section, you will be able to explain the importance of testing in software engineering. Describe the types of tools used by software engineers. Describe ways that software reuse is made possible. Explain the role of ethics in software engineering. Discuss the future of software engineering. The role of a software engineer is wide-ranging, and the factors that impact software engineers are many. There are a few areas, however, that are worth delving into deeper. These areas include software testing, refactoring, design patterns, software tools used in software development, software reuse, free and open source software, FOSS, software engineering ethics, and legal aspects. Testing. The purpose of testing is to verify that the software being developed delivers on the requirements that were set for the project without any unintended errors or side effects. In simple terms, it is to make sure software does what it was expected to do. Through this process of confirming that the software meets expectations, any issues that are found can be resolved to ensure the integrity of the product. Testing should happen within nearly every phase of a project, with each phase having a specific testing focus. One axiom of testing is to test early and test often. As can be seen in Figure 9.17, the earlier issues can be found when developing software, the less costly they are to fix or resolve. Issues are generally found as a result of testing. Relative cost to fix bugs, based on time of detection, graph shows rising costs starting at 2x at requirements architecture, coding, integration component testing, system acceptance testing, rising to 30x at production post-release. Figure 9.17, the cost of finding issues rises through the life of a software development project. For example, the later a bug is found, the more it costs to fix. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Levels of testing. Software goes through various levels of testing to ensure quality. Unit testing. Individual software components, functions, or methods are tested in isolation to verify they work as intended. Integration testing focuses on interfaces between components, ensuring they work together seamlessly. System testing tests the entire software system as a whole, verifying it meets overall requirements. In addition to the various levels of testing, there are other crucial testing approaches that are used to ensure that software delivers to expectations. These approaches include acceptance testing, verifies that the software meets the expectations and requirements defined by the client or end users. Usability testing evaluates how easy and intuitive the software is for users to interact with. Stress testing assesses how the software performs under heavy loads or unfavorable conditions. Performance testing evaluates the speed, responsiveness, and scalability of the software under various conditions. Security testing identifies and addresses security vulnerabilities to protect against unauthorized access or data breaches. Some testing is done by software developers, including software engineers who write code, but a majority of testing is done by quality engineers whose primary focus is testing. End users can also participate in acceptance testing or user testing scenarios. Concepts in practice. How does Microsoft test Windows before release? Microsoft uses millions of testers before deploying a new update of Windows. These testers are a part of the Windows Insider program and have access to the pre-release versions of Windows. Anyone can sign up for this program. They just need to agree to test the new version and provide Microsoft with feedback. Because testing is done on a pre-release version of the software, the testers know that the software may be unstable and will likely have issues. If you are curious about testing or are interested in becoming a tester yourself, visit Microsoft Windows Insider or Apple's beta software program for more information. Methodologies of testing. There are 3 primary testing methodologies, and they are categorized by the knowledge the tester has or needs to have to conduct the tests. The 3 methodologies are: the manner of testing, where the tester is aware of the code, so they can test that the internal structure of the item being tested works properly, is called white box testing. Other names for white box testing include glass box, clear box, and structural testing. Tests based on requirements and the functionality of what is being tested without the need to focus on the code itself is called black box testing. The tester does not need to have any knowledge of the code. Other names for black box testing include input-output testing, specification-based testing, and behavioral testing. The hybrid of both white box and black box testing is called gray box testing. The person who designs the test has a partial knowledge of code structure and understands the intended design of the software. When testing at the testing system level, we distinguish between verification and validation. Testing that the software solution functions without errors is called verification. In organizations that have large development teams, verification is often done by a quality assurance (QA) team, testing that the software solution conforms to the requirements and does what the user wants it to do is called validation. Both verification and validation require code execution and can happen in all levels of testing, with verification generally taking place before validation. Testing is also distinguished by purpose into functional and non-functional testing. With functional testing, the functionality is tested. With non-functional testing, qualities such as performance, scalability, and usability are tested. The attributes of a good test are as follows. A good test has a high probability of finding an error or issue. A good test is not redundant. It does not test the same thing as another test. A good test should be neither too simple nor too complex. Unit testing. A crucial role in software development. The process of unit testing involves testing individual units of code, such as methods and functions, and it is usually done by developers during the development of the software or when updates are made. Software developers write scripts or code that test the functionality of a specific piece of code. Unit tests are typically added to a regression test suite, so they can be run again after each change to the source code to verify that the change did not break any existing functionality. Imagine a function that calculates the area of a rectangle. A unit test would verify that the function returns the correct area for different width and height values. Unit testing offers several benefits. Early bug detection. Unit tests help identify bugs early in the development process, when they are easier and less expensive to fix. Improved code quality. The process of writing unit tests encourages developers to write clean, modular, and well-documented code. Maintainability. Unit tests serve as living documentation, clarifying the intended behavior of code components and making future modifications easier. Concepts in practice. Staying in their lane. In the automobile industry, most new cars now include a lane detection system, LDS. This system includes code that verifies video images that are received by the automobile. The software checks to see if the vehicle crosses one of the lines painted on the road. If so, it activates a warning system to let the driver know. Units test for such a system include the following. An appropriate line is recognized. A warning occurs if a line appears to be crossed. The warning ends after the designated period of time. When the LDS system is turned off, the warning is not triggered. Software engineers as well as testers perform these tests when the code for the LDS system is created, as well as anytime any updates are made to the system. Code coverage. Proper unit testing improves the quality of a software system and helps discover bugs early. In simple terms, a software bug is an issue or error with software programming. To find bugs, it is important to review and run the code. The range of a unit test is typically measured in terms of code coverage, which is the measurement of the percentage of code that is activated or reviewed by the test. Common types of code coverage are statement coverage, line coverage, and path coverage. Measurement of the percentage of statements that are activated at least once when you run all tests is statement coverage. Measurement of the percentage of activated lines of source code that are tested is line coverage. Measurement of the percentage of paths through source code that you go through is path coverage, as shown in Figure 9. 18 with path coverage, if you have two conditional statements, one after the other, there are typically 4 paths through this code. Both conditions are true. The first condition is true and the second is false. The first condition is false and the second is true. Both conditions are false. Code path illustration of 4 paths, I, X, and Y positive, Roman 2, X positive, Y negative or 0. Roman 3, X negative or 0, Y positive, Roman 4, X and Y negative or 0. Figure 9. 18 This activity diagram illustrates how path coverage works with 4 possible paths. I, X and Y positive, Roman 2, X positive, Y negative or 0, Roman 3, X negative or 0, Y positive, and Roman 4, X and Y negative or 0. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Path coverage is more demanding and typically requires more tests than statement or line coverage, but tests are better. You need a minimum of 4 tests to achieve 100% path coverage, but a minimum of 2 tests to achieve the same level of statement coverage. Support for unit testing. Unit testing is so common that major programming languages provide some support for automated unit testing. An example is JUnit, a unit testing framework for the Java programming language, which is shown in Figure 919. JUnit facilitates the writing and managing of tests, and it can be run in some development environments quickly, typically via a single click. Many of the other major programming languages have similar frameworks or tools. There are also third-party software products that can be used to help with unit testing. Screenshot of JUnit window with green arrows for tests run. Figure 9. 19 JUnit test window in NetBeans Integrated Development Environment, IDE. You can run all tests by clicking on the green arrows. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. Credit, NetBeans by Sun Microsystems. Test-driven development. Many organizations use test-driven development, TDD, which is a process where developers write tests before they write the code. This might seem counterintuitive, but it offers several benefits. Clarifies requirements. Writing tests first forces developers to think critically about the problem they are trying to solve and the expected behavior of the code. For example, if you are to write code that finds real roots of a quadratic equation, and you start with unit tests, you will probably identify 3 cases that must be solved separately. The case when the equation has 2 roots, the case when the equation has a single root, and the case when the equation has no root. Facilitates early bug detection. Writing tests first helps identify bugs early in the development process, when they are easier and less expensive to fix. Results in improved design. The test-driven approach can help identify edge cases and scenarios that might be overlooked during traditional development, leading to a more robust design. Results in improved code quality. The focus on writing clear, testable code leads to overall higher code quality. As illustrated in Figure 920, in test-driven development, you write unit tests first. You then run the tests, which should fail because there is not a fully implemented function to test against. You will then run and rerun the tests as you develop the functions. Development continues until all of the unit tests pass. Circular graphics start 1 write test, 2 test fails, 3, write code, 4 test passes, 5, refactor, 6 test passes, code complete. Figure 9. 20 In test-driven development, the developer writes the test before writing the code. Thus, when the test is first run, it should fail. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. Here's a breakdown of the steps of the test-driven development process. Write a test. The process starts with the developer or development team writing a unit test that defines the expected behavior of a specific function or code unit. Run the test and see it fail. Run the test. Initially, the test will likely fail because the function it tests doesn't exist yet or isn't implemented completely. Write just enough code to make the test pass. Focus on writing the minimum amount of code necessary to make it pass the test. Run the test and see it pass. When the code passes the test, this ensures it is fulfilling the intended functionality defined in the test. Refactor, improve code structure. Once the test passes, take a step back and refactor the code to improve readability, maintainability, and overall code structure without changing functionality. The process of restructuring source code without changing its functionality is called refactoring. We typically use refactoring to make code more readable. This can be as simple as renaming a variable or as complex as breaking the function up and splitting it across modules. Once the refactoring is complete, the unit tests should be executed again to make sure the code continues to pass. Run tests again. After refactoring, run all tests again to verify the code continues to pass and ensure no unintended side effects were introduced during refactoring. Once you're done with all the steps, start the cycle over. Repeat this cycle: write test, write code, refactor, run test for each unit of functionality you develop. System testing. Whereas unit testing focuses on the various units or pieces within a software solution, system testing focuses on the complete and fully integrated software product. The overall goal of system testing is to make sure the complete software solution works on the whole as expected. This is generally a black box style of testing that focuses on making sure the software meets all the requirements that were determined and checks that any possible scenarios that could be applied to the software function play out as expected. System testing is generally done by testers rather than the end users of software, and it involves reviewing both functional and non-functional requirements. System tests can be performed by testers, or they can be automated. The form of system testing where a person must run the software system, provide any input, and manually check all output is called manual testing. Repeating tests requires these efforts to be repeated by the tester. The form of testing where a program or code is executed that tests the functionality of a software system or some of its parts is called automated testing. It allows for repeating tests without requiring repeated effort on the part of the tester. An example of such a program is Selenium. Selenium is a suite of free tools that automates the testing of web applications. The easiest way to use Selenium is to have it capture the interaction between your browser and web application. The interaction is saved as a script. You can then edit the script if needed and replay it to check if the web application still works. Selenium also provides libraries for many popular programming languages, including Java, C, and Python, that allow users to write programs that perform this testing. Acceptance testing, also called user acceptance testing. Acceptance testing is the process used to determine whether the software solution fulfills the customer's expectations. This level of testing generally occurs after system testing and is done by the customer, client, or other end user of the software. Acceptance tests are formalized testing that can be specified by the customer, and it tests both functional and non-functional requirements. To test functional requirements, acceptance tests often follow scenarios created in requirements analysis. For example, in a library information system, we can use scenario add new book to create an acceptance test. During the acceptance test, the tester will fill out an input form, submit it, and check that the system contains a new book. In the automotive industry, acceptance testing could be done by the department that requested the new features. It could also be done by dealerships or customers who own or have purchased previous versions of a given automobile. A driver could be asked to use the new features and then be surveyed to see what issues occurred. Usability testing. The user-centered testing method that evaluates how easy and intuitive a software system is to use is called usability testing. It goes beyond just ensuring the software functions correctly and focuses on the user interface user experience, UI/UX, the part of computer programming that concerns how information is presented to the user and how the user can interact with a program. Usability testing is essential because software that is difficult to use can frustrate users and hinder adoption. By identifying usability issues early in the development process, developers can make improvements that lead to a more user-friendly and successful product. Usability testing typically involves recruiting a small group of users representative of the target audience. These users are asked to complete a series of tasks while a usability tester observes their actions and records their feedback. The tester pays close attention to areas such as task completion, Can users complete the intended tasks efficiently and without errors? Ease of learning. How easy is it for users to learn how to use the software? User satisfaction. Are users satisfied with the overall user experience? While acceptance testing generally happens near the end of a project, usability testing can and should happen much earlier. The focus of usability testing is to enhance user experience, and it typically emphasizes the following areas: interactivity. Are interaction mechanisms, e.g., menus, buttons, clear and consistent? Do they provide appropriate feedback to user actions? Layout. Is information organized in a logical and easy-to-find way? Can users navigate the system intuitively? Readability. Is text easy to read and understand? Are error messages clear and actionable? Aesthetics. Is the overall look and feel of the software pleasing and consistent? Do colors, fonts, and images contribute to usability? Display usage. Does the software solution use the best possible screen size and display resolution? Timing. Are important features and other pieces of functionality quickly accessible? Feedback support. Is useful feedback provided to end users, and can they easily go back to their work once the feedback has been read? Personalization. Is the application addressing various categories of users, and does it support inclusion? Help. Is it easy for users to access help and other support options? Accessibility. Can the software be used by people with disabilities? This includes features such as screen readers and keyboard navigation. Note that accessibility testing is a subset of usability testing that focuses specifically on the needs of users with disabilities. Here are some examples of accessibility considerations. Screen reader compatibility. Can screen readers interpret the content and functionality of the software accurately? Color contrast. Does the software use sufficient color contrast to be usable by people with visual impairments? Keyboard navigation. Can all features of the software be accessed using only the keyboard? Content features. Is blinking, scrolling, or auto content updating avoided to accommodate users with reading difficulties? Industry spotlight. Usability and acceptance testing by car manufacturers. Usability and acceptance testing are quite different. Let's consider again the software for the lane departure systems, LDS, that are incorporated into automobiles these days. Acceptance testing would confirm that the lane departure system works as expected. Did the warning happen when a vehicle crossed a lane line? Did the software recognize when the vehicle departed the lane? Did the system warning start and end in an amount of time that was appropriate to the user? When the system is disabled, did the software ignore lane departures and not trigger the warnings? With usability testing, the focus is more on whether the system met the expectations of the users interacting with it. Was the system usable? Did the user use the feature as intended? Did the user react appropriately to the warning signal? Was the signal so startling it caused the user to jerk and risk an accident? Did the user simply turn off the system because they found it annoying? The focus of usability testing is on how the solution is being used and whether it was created in the most intuitive manner. The Insurance Institute for Highway Safety found that 49% of users turned the LDS off during their normal commuting. More important, it was found that 54% turned it on if it used tactile warnings, compared to only 46% turning it on if it used an audible alert. From a usability testing standpoint, this shows that it is better to focus on a tactile warning over an audible one if the goal is to get the most usage. Because LDS has been shown to decrease the chance of fatal accidents, even with low usage, it can still help save lives. Software engineering tools. Software developers use many tools that facilitate development. Some of them are used daily, while others only occasionally, but they all play an important role in software engineering process. Compiler. A compiler is a program that converts source code into a syntax or format that a computer can execute. Programming languages such as C and C++ compile into machine code, which consists of instructions for a specific processor. Other programming languages, such as Java, compile into machine-independent code. For example, Java program code is generally compiled into Java bytecode. This machine-independent code is then executed on a Java virtual machine. Debugger. A debugger is a program that assists in detecting and correcting of bugs. It typically helps in finding issues in code by enabling features, such as the ability to halt a program, while it's running so that variable values can be displayed and even changed. Debuggers can also run a program line by line to see what each line of code is doing. More advanced features involve halting a program on a specified condition and checking for deadlock and memory leaks. Figure 9. 21 shows the NetBeans debugger stopped on line 6 of a program. In the lower part of the screen, the software developer can see the values of the variables currently used by the program. Screenshot of a debugger tool from NetBeans. Figure 9. 21 In this debugger tool from NetBeans, the program stopped at line 6, creating an opportunity for the developer to choose what to do next. The lower window displays the values of variables currently used by the program, rendered in NetBeans by Sun Microsystems. Attribution: Copyright Rice University, OpenStax, under CC by 4.0 license. Profiler. A profiler is a program that performs dynamic program analysis that can be used to optimize or otherwise streamline code. It collects data such as frequency and duration of method calls and presents it to the software developer, who can use it to propose code optimizations. The process of data gathering is called profiling, and it is typically performed when the performance of the software system does not meet specified criteria. Integrated Development Environment, IDE. Software engineers typically write source code in an IDE such as IntelliJ, Microsoft Visual Studio, or VS Code. An IDE is a software application that facilitates software development by combining several tools that developers use, such as an editor, compiler, debugger, and profiler. Some IDEs only support a specific programming language, such as IDLE for Python, and some support multiple programming languages, such as Microsoft Visual Studio, which supports C++, C, Visual Basic, and JHash. The best IDEs provide features that facilitate writing and maintaining source code. These features can span from simple features, such as syntax highlighting, to sophisticated ones, such as static analysis of source code. Syntax highlighting displays different parts of the source code in different colors, which facilitates reading. Figure 9. 22 shows an IDE highlighting Java code. Screenshot of code highlighted in different colors in a window. Figure 9. 22 Syntax highlighting is a feature of IDEs that helps developers read code. Here, Java source code is being highlighted by the NetBeans IDE, rendered in NetBeans by Sun Microsystems. Attribution: Copyright Rice University, OpenStax, under CC by 4.0 license. The cost of IDEs can range from free to thousands of dollars. IDEs such as Eclipse, NetBeans, and Microsoft Visual Studio Code are free. Microsoft Visual Studio and IntelliJ IDEA have a fee associated, although there are free editions of each available. Generally, the cost of an IDE is offset by the increase in productivity that a developer gains from its use. Version control system. A quite common tool used in software development is a version control system, which stores the history of changes to source code and facilitates collaboration of multiple developers. The most popular version control system today is Git, which is often used with a common hub, such as GitHub or Bitbucket. Git stores the project source code written by a developer in a repository that is typically on the developer's machine. Developers can push their code to a project repository for integration purposes. The main features of Git are as follows. It tracks changes in your source code. It enables reverting the changes. It facilitates collaborative development. GitHub facilitates code sharing among developers by allowing developers to modify source code on their own machine, commit changes to a Git repository on their machine, and then push changes from their machine to GitHub so that other developers can access them. Many open-source projects are hosted on GitHub that allow people to download their source code and contribute. Figure 9. 23 shows a standard GitHub page, in this case from the JavaScript library called the jQuery project. Screenshot of a GitHub window. Figure 9. 23 GitHub is a version control system that facilitates code sharing among developers. Credit: GitHub CC01. 0. Bug tracking system. Another common software development tool is a bug tracking system, which aids in the tracking and resolution of fixing issues with software. Bug tracking software stores information about issues that have been reported and their resolution. A common workflow with the bug tracking system is as follows. When a customer or a tester reports a bug, a new record in the bug tracking system is created. Then, the project manager or any other team member assigns the bug to a developer. The bug report must provide instructions as to how the bug manifests and may be fixed so that the assigned developer can reproduce it and decide how to proceed. Here's a general breakdown of how bug tracking works. If the bug cannot be reproduced, or if it is not a bug but a request for a new feature, it will be rejected. If the report describes a bug that was already reported, it will be marked as a duplicate. If the fix is scheduled for a next release, it will be marked as deferred. When the developer fixes the bug, the code should be retested to confirm that the bug has truly been resolved. Figure 9.24 illustrates a common bug reporting and tracking flow. Bug tracking chart: new, assigned, opened, fixed, duplicated, rejected, deferred, retested, verified, closed. If reopened leads to assigned. Figure 9.24 The Jira issue tracking system shows a common workflow of bug tracking systems. When a bug is detected, a new record is created. After the bug has gone through the process of being assigned and fixed, and the fix has been verified, the record closes. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 9.25 shows a bug tracking tool, the jQuery bug tracking tool, that is available on GitHub. Screenshot of jQuery bug tracker on GitHub. Figure 9.25 The jQuery bug tracker on GitHub keeps track of how many issues are pending, 86 open, and which have been resolved, 602 close. Credit GitHub CC010. Industry Spotlight. Bugs not caught. In January of 2022, the San Francisco Unified School District rolled out a new employee information system, which included the payroll for over 10,000 employees. Unfortunately, the development team did not do a thorough job of testing this system, and it contained a number of bugs when it was launched. As a result, hundreds of teachers and staff members did not, even after several months, receive paychecks from the system. Because the system was unable to process payroll, hundreds of employees were unable to pay their rent, medical bills, and other expenses. In this case, the delivery of a flawed system harmed people. This is an example where a systems product did not adhere to the highest standards and failed to be tested to a level that would avoid an issue that directly harmed many of the employees who relied on the system. While the Chief Technology Officer issued apologies and assigned 100% of the project staff to get the issues resolved, the reality is, and ethically speaking, more time should have been allotted to test the system prior to it replacing the old system. We typically think about all of the ways that technology and systems can help people. It is also important to acknowledge there are risks also. Bugs in software can have a significant impact on the people affected. This reinforces the importance of testing and validating a system before we release it. Software reuse. When constructing software, developers commonly use libraries and frameworks, which consist of code that was written by other developers. Libraries typically provide some functions, which you can call in your code, and frameworks typically provide application skeletons, which can call your code. For example, you can have a library that provides encryption functionality and a framework that facilitates the development of web applications. Both libraries and frameworks are common in software development, and it is common to combine them. Libraries can be static, which are linked to your code at compile time, or dynamic, which are linked to your code when it executes. Because static libraries are linked at compile time, you must recompile the program when the library is modified. On the other hand, a dynamic library is in a separate file, and thus it can evolve independently of your code. Some programming languages, such as Java, provide ready-to-use code as part of a language library. That code may be invoked via an application programming interface, API, and it involves implementation of common data structures and operations on them. Software applications may also leverage external APIs that allow developers to access functionality or data. For example, the United States Postal Service, USPS, provides an API that can be used to get shipping rates, track packages, schedule package pickups, and more. There is no need for a developer to write new code to do this, but rather they can tap into the USPS API instead. It might seem that we do not need to write code anymore because we can assemble applications from existing components, but unfortunately, it does not work this way. One of the reasons is that we usually want to customize functionality, and another reason is that even if an existing component is a good fit for a project, we are often not allowed to use it due to legal reasons. Each component is published under legal terms called licenses, and if we want to use it, we must follow these terms. For example, components published under the GNU General Public License require software that uses them to be published under the same license, which is usually not acceptable in commercial environments. Technology in everyday life. Libraries on your computer. Code reuse and the use of libraries is extremely common. In fact, if you look at the files on a Microsoft Windows computer, you will find that a plethora of libraries are used by the Windows operating system itself. The files that have an extension of DLL are library files where DLL stands for Dynamic Link Library. On a computer running Microsoft Windows, do a search in Windows File Explorer using *. DLL to view a list of dynamic link libraries. Notice how many there are and the dates they were updated. Many of the Windows operating system files are DLL files that get updated at a different frequency as compared to the operating system. The names of some of the files will give you an idea of what the code within them likely does. You can, of course, attempt a similar search for a computer running on Apple's operating system. Pattern. A pattern is a high-level concept that supports the idea of reuse and provides reusable solutions to problems often encountered when building software. Patterns are not backed up by any theory. They relate to solutions that were observed in practice at various levels of abstraction and proved successful. In general, patterns are discussed in terms of their meaning, their intent, and the benefits of using them across many software engineering areas. Patterns are typically organized hierarchically in pattern catalogs using descriptive pattern templates. Pattern languages may be used to describe the compatibility between various patterns and help weave them together whenever applicable. Software engineers are likely to encounter two broad categories of patterns, depending on whether they are designing a software architecture model or mapping it to a corresponding implementation architecture tailored to the platform or environment the solution is meant to be deployed onto. Patterns used to model software architectures include architectural style, architectural patterns, and design patterns, an architectural model, or an implementation of such. As you learned earlier in the chapter, an architectural style is a transformation that is imposed on the design of an entire system. The intent is to establish a structure for all components of a system under development. Examples of architectural styles for distributed systems include the Object Management Architecture, OMA, Service-Oriented Architecture, SOA, Multi-tier Architecture, and Peer-to-Peer Decentralized Architecture. Note that multiple architectural styles may be combined to create a hybrid architecture style. An architectural pattern is part of a category of patterns that focus on the architecture of software. They tend to be more abstract and focused on improving issues such as deployment, availability, maintainability, performance, scalability, security, and testing. A design pattern is a reusable solution to a design problem that software engineers repeatedly encounter while architecting and designing software systems. For example, the design pattern singleton suggests how to restrict the number of class instances to one. This problem commonly occurs in software systems whenever a class represents a thing or concept that has a single instance. A more complex design pattern is builder, which allows a software engineer to create an object in steps and is typically used when creation is a complex process. Furthermore, a design pattern imposes a transformation on the design of an architecture of a given architectural pattern. Therefore, architectural and design patterns may be used in conjunction with an architectural style to shape the overall structure of a system. For example, Model View Controller (MVC) is a typical architectural pattern that is used to design the software architecture of a multi-tier system. If the multi-tier system provides a scoreboard, that feature will leverage a singleton design pattern to avoid confusion and ensure the existence of a single scoreboard. There are many design patterns described in software development literature. The first book collecting design patterns by Gamma, Helm, Johnson, and V. Lisides, was written in 1995 and continues to be available today. More patterns have been identified and shared since that time. You can find many listings of commonly used design patterns online, such as the one available on the Tutorials Point website. Each design pattern provides a solution to a problem in a particular context. Thus, design patterns are not universal solutions, as they almost always come with disadvantages, and it depends on the context whether the advantages outweigh the disadvantages, which is why it is important to not only be familiar with design patterns, but also to understand their advantages and disadvantages so that you can assess their benefits and drawbacks in a specific context. Design patterns can be applied when you design a software system, or they can be introduced later on in the process of refactoring. They are rarely applied in their pure form as they are described in literature. The more common practice is to tailor them according to the context in which they will be used. It is also common that the code base of a software system may implement several design patterns, which contributes to the superior quality of the system. Refactoring. As has been stated earlier, refactoring is the process of restructuring source code without changing its functionality. It is not specific to reuse, though refactoring can involve reuse. Typically, refactoring consists of making a series of elementary changes called micro-refactorings, such as rename an attribute, which changes the name of an attribute to a new one that better corresponds to its purpose. Rename a method, which changes the name of a method to a new one that better corresponds to its purpose. Extract a class, which moves a part of an existing class into a new class. Extract a method, which moves a fragment of code into a new method. Inline a method, which replaces a method call by its body. This is typically used only for very short methods. Move a method, which moves a method to a more appropriate class. Move a field, which moves a field to a more appropriate class. Remove dead code, which removes code that never executes. Replace a literal with a symbolic constant, which replaces a magic value with a named constant. Change method parameters, which adds or removes method parameters. Substitute an algorithm, which replaces one algorithm with another. This is typically done to improve performance of the software system. You can apply these micro-refactorings manually, but it is more common to perform them in an IDE. Modern IDEs provide support for some refactoring, and you can often apply a selected refactoring by activating an appropriate menu item, as shown in Figure 9.26, screenshot of NetBeans IDE. Open window is highlighting refactor, which opens to window with rename highlighted. Figure 9.26 in the NetBeans IDE, the action of renaming a method falls under the refactor menu item. Rendered in NetBeans by Sun Microsystems. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Returning to the concept of reuse, one of the benefits of refactoring is that functions, classes, and other chunks of code can be extracted from other parts of the code. These can then be reused by placing them in libraries, by incorporating them into a framework to be used by other developers, or by constructing an interface to access them. Software licensing. When software engineers design and develop software for an organization, that software and all its code generally belong to the organization. This means the source code and functionality cannot be used by others without permission. This permission is typically controlled by a software license. The type of license can be determined by those who created the software or commissioned its creation. Two of the most common categories for defining software reuse are closed source and open source. Proprietary or closed source software is a form of licensing that prohibits access to underlying source code. This type of software is typically developed for organizations or as software to be sold. It can be used to protect software that might contain proprietary information or intellectual property within the code. Free and open source (FOSS) or open source software is a form of software licensing that provides access to the underlying code and generally allows the code to be reused and modified. It is important to read the license terms of any software code used. It is also important to make sure that, if software is to be shared, it is clear as to what license will be applied to both the use of the software and its code. If a license is not provided with code, then the code is generally protected under copyright rules. Free and open source software (FOSS). Free software, sometimes called Libre software, is software distributed under the terms that provide users with the following 4 freedoms. The freedom to run the software for any purpose. The freedom to study how the software works and modify it. The freedom to redistribute the software. The freedom to improve the software and release the improvements to the public. The freedom to study how the software works and modify it, and the freedom to improve the software can hardly be fulfilled without source code. And so these freedoms more or less imply that source code of the software must be available. Free here refers to liberty, not price. You may be required to pay for free software. Software that is distributed gratis is referred to as freeware, and it rarely comes with source code. Open source software is software distributed under a license that grants users the right to use, study, modify, and distribute the software and its source code. It does not mean that software must be gratis, although in many cases it is the case. Today, it is common that open source projects provide their source code via a public repository on the internet that allows anybody to contribute. The benefits of FOSS are as follows: improved quality and reliability. Community involvement in open source projects can lead to better quality and more reliable software due to a wider range of users and developers identifying and fixing bugs. Lower development costs. Open source software can benefit from community contributions, reducing development costs for companies and organizations. Innovation. Openness and collaboration can accelerate innovation as developers can build upon existing open source code. Some projects that were developed as free and/or open source software can be categorized as follows. Operating systems. Linux, an open source operating system, which is distributed in so-called distributions. The distributions are referred to by names such as Debian, Fedora, Ubuntu, Red Hat, and SUSE, and they can be commercial paid or community-driven gratis. The Linux kernel is licensed under GNU General Public License, version 2, which makes it a free and open source software. Android, a free and open source operating system developed by a consortium sponsored by Google. It is based on the Linux kernel and other open source software, and it aims primarily to touchscreen mobile devices, such as smartphones and tablets. Android is the most common operating system, not only on mobile phones. Development tools. NetBeans IDE, an open source IDE that started as a student project with the goal of creating an IDE for the Java programming language. Now it belongs to Apache Software Foundation and also supports other programming languages such as PHP, C, C++, and JavaScript. Eclipse IDE, an open-source integrated development environment that started at IBM and is now managed by the Eclipse Foundation. GNU Compiler Collection, GCC, a free and open-source compiler, or more precisely a suite of compilers that supports various programming languages, hardware platforms, and operating systems. It is the standard compiler included in many Linux distributions. Web browsers. Google Chrome, a no-cost web browser developed by Google. Although most source code of Google Chrome comes from free and open-source software, it is licensed as proprietary freeware. It is available on Windows, Linux, Android, macOS, and iOS. Mozilla Firefox, a free and open-source web browser developed by Mozilla Foundation. It is available on Windows, Linux, macOS, and Android. Programming languages. OpenJDK, a free and open-source implementation of the Java platform, Standard Edition. Many other distributions of the Java platform, such as Amazon Corretto, are based on OpenJDK. C#, a modern cross-platform programming language initially developed by Microsoft. Both the C# language and the current, as of 2014, Microsoft C# compiler are open source. Python. A modern programming language that is completely open source, freely usable and distributable, even for commercial use, making it extremely popular with businesses around the world. Application servers. Payara server, an open source application server with paid support options. While some open source software is entirely free, FOSS projects can have successful business models. It may seem that open source software development does not bring any benefits to software publishing companies, but community involvement leads to better quality and higher reliability of the software and lower cost of development. Many software companies that moved to open source development adequately modified their business model, and instead of selling software, they charge the customer for providing additional services. For example, Payara Server is an open-source application server for Jakarta Enterprise Edition applications. The server is gratis, but companies that use Payara Server for mission-critical applications can pay for support, which allows them to consult a team of software engineers at any time. In addition, they receive monthly releases with bug fixes and security alerts. Many companies that embrace open-source development focus on providing value-added services, such as technical support, training, or custom development, around the core open-source product. It is important for companies and developers to pay attention to the following: software licensing considerations. Understanding software licenses is crucial for both software users and developers. While many people accept end-user licensing agreements, EULAs, when installing software on their personal computers and devices, it is important that software engineers understand that these are legal agreements. As such, when using software to build solutions, it is important to understand what the licensing allows. Using open-source software, software developers should be aware of the license terms associated with any FOSS they use to ensure compliance. Distributing software. Additionally, when distributing software, it is important to make sure that an included license defines how you or the organization that owns the software wants it used and protected. Choose a license that aligns with your project's goals and how you want your software to be used and distributed. FOSS is a powerful development model that fosters collaboration, innovation, and cost-effective software creation. While security considerations should also be factored in, open-source software plays a vital role in the tech industry. Software engineering ethics and legal aspects. Software engineers often spend a lot of time creating code and solutions to solve problems. While they might be the ones writing the code, that does not mean the code or the knowledge that they gained while writing the code belongs to them. For example, if a software engineer worked for an auto manufacturer, they might be tasked with designing and creating a futuristic product that detects the eye movement of a driver to verify they are looking forward while driving. The software might present an alert if the driver's attention wanders from the road for longer than a given period. Generally, it would be considered unethical for this same developer to use what they learned while working for the auto company to develop their own software product that uses the same code to detect eye movement. While the software engineer might have written the code, they wrote it for the auto company, so it would be unethical to use the same code in an independent product without the auto manufacturer's permission. Software engineers should abide by a code of ethics that guides the work that they do and the products that they produce. At a personal level, ethics for software engineers involve the following guiding principles. Do not use other people's data or code for financial gain. Do not leverage other people's proprietary information as part of a commercial project. Do not use or hide the use of other people's data or programs as part of your own projects. Do not violate the privacy of others. Do not gain wrongful access to a system for financial gain. Do not create or propagate computer viruses or worms. Do not create or use programs that promote discrimination or harassment of any kind. The Association for Computing Machinery, ACM, and IEECS established the Committee on Professional Ethics (COPE, which published a software engineering code of ethics and professional practice. This code of ethics states that software engineers shall commit themselves to making the analysis, specification, design, development, testing, and maintenance of software a beneficial and respected profession in accordance with their commitment to the health, safety, and welfare of the public. The code goes on to define 8 principles that all software engineers are required to follow to possibly avoid legal consequences. Responsibility should be taken for the work done. Actions should be in the best interest of a client or employer. Products and updates should be created in a manner that adheres to the highest professional standards. Integrity should be applied in actions taken. An ethical approach to managing software development and updates should be maintained and promoted. The integrity of what it means to be a software engineer should be maintained. Software engineers should be supportive of peers and colleagues in a manner that is fair. Learning should be a continual endeavor to the betterment of the software engineer's own profession. Link to learning. You can find the full code of ethics and professional practice on the ACM website. This includes an overall preamble as well as details for each of 8 guiding principles. Think it through. Applying the concepts of ethics. As a software engineer, you will deal with the constant change of technology and the constant need to understand a variety of business scenarios to build solutions. Clearly, you cannot be expected to know everything. Consider 2 hypothetical scenarios. In the first, suppose that a developer, when faced with a task they did not know how to do, spent days avoiding the rest of the team as they researched and read books to try to learn the new technology. They did not tell anyone they did not know the technology. In the second, imagine a developer was faced with the issue of needing to code for a widget for the team to use. The issue was shared online in developer forums such as Stack Overflow and Code Project, and the developer asked others to provide code to do what the widget was expected to do. While the developer did not understand what the code did, he copied what he was given and presented it to the team as his own without saying where it came from. In both situations, how did the concepts of ethics apply? Road ahead for software engineering. People have vastly different opinions as to what software engineering will be like 20 or 30 years into the future. One day, revolutionary discovery or invention may change our society in a radical way, or not. Nobody can predict when or what specific scientific breakthroughs will happen, and discoveries can shape our future in ways that are hard to imagine today. Based on our experience of the past 20 or more years, however, we can make some predictions about where software engineering may be in 2040. Evolution of programming. We can, for example, predict that the evolution of current programming languages will be driven by changes in hardware, and that the tools developers use will improve. But with the evolution of AI and machine learning, will software developers become obsolete? Under current circumstances, the answer is no. AI can, however, help with some developers' tasks, such as testing, debugging, and refactoring. While we can expect that intelligent bots will be members of development teams, they will not fully replace software developers. Future of software development. Now let's discuss 3 questions about the future of software development. What programming languages will we use? we can expect that current programming languages will evolve, perhaps even become obsolete, by 2040, but it is hard to imagine that languages like Java, Python, C, and C++ will disappear entirely because there is so much code written in these programming languages. Can we get to the point where all software is written and we do not need any software development? Absolutely not in the near future. We are not at the end nor in the middle of a technology revolution. We are at the beginning. The importance of software in society will grow, and software systems will become more sophisticated. For example, with the Internet of Things, IoT, we will connect thousands and thousands of smart devices to the Internet, and they all will need software. Does it make sense to learn programming today? Absolutely. With the increased use of smart, connected devices, the integration of technology is getting more rather than less prevalent in almost all facets of life, and technology continues to offer an advantage to businesses to operate quicker, better, and more effectively than the competition. Given this, software development will become more important. Additionally, electronics, including computer hardware, and the way computer programming is applied continue to evolve. In the early 2000s, mobile computing and Wi-Fi connectivity changed the way computing happened. In the past decade, connectivity continued to evolve, and many new types of smart devices needed new code. Over the next few decades, changes in the core of computers, such as the creation of quantum coprocessors, have the potential to revolutionize software development yet again. In 2021, the U.S. Bureau of Labor Statistics predicted that over the next decade, the number of software engineering jobs in the United States will increase by 25%. This is in part because technology continues to infiltrate our daily lives. For example, many grocery chains are updating their shopping carts to include sensors that record all of the items you add to the basket area. As this automation continues and expands, it will require a lot of software developers. The current push for autonomous vehicles will be accomplished as a result of sensors and a large number of software engineers creating hundreds of thousands of lines of code. It will take years of testing, debugging, and refactoring before autonomous vehicles are as commonly accepted as a mobile phone is today. It will be software engineers who make that happen.